Hello, everyone. Good morning, good afternoon, good evening, good night, wherever you are. I'm Avi Sporer. I'm co-chairing the SOC together with Jennifer Burt, who is also here. Welcome to the second TESS Science Conference, which is, of course, fully online due to world events. I want to start by thanking the many people on the SLC and the LOC for all their work during the last few weeks and months. I also want to acknowledge the wide range, the international range of participation in this conference. This is the geographical distribution of people who registered to the conference, and it also shows the international interest in the TESS mission. This is, by the way, an interactive map. It's on the website. You can go and play with it even right now and zoom in a bit and see the more specific detailed location of all the participants. I want to use this few minutes to just give some the logistical information so you can enjoy all the components of the conference. So first thing is about the Zoom links. I'm sorry. First thing is about the off-topic talks that we have. Off-topic, we mean these are talks that are not directly related to TESS Science, but are of interest to the audience and participants of this conference. So they will be on the light side, or dare I say, fun side. And they were added relatively recently, last week. So the first is on the connection between art and science communication. It will be given by the team that is doing and producing the JPL travel posters. That here are two examples. We've all known them. This talk will be given tomorrow on Tuesday. And this is well-timed with a new release of a new batch of posters by the JPL travel posters team. And they did tell us that one of those new posters will be about the TESS mission. So I hope that is enough of a teaser to make you interested and come listen to that talk tomorrow. The second off-topic talk will be about the NASA Juno mission to Jupiter, which is ongoing. It will be given on Wednesday by Stephen Levine, who is the Juno project scientist from JPL. This talk is also well-timed. We didn't plan for it, but it just happens to be that this week is the 10th anniversary of the Juno mission launch, which was in August 5, 2011. So we asked Stephen Levine to give us a tour of the scientific discoveries and achievements of the Juno mission so far. Okay, now I want to turn a bit to some logistic information. The links to all our virtual rooms, all the Zoom rooms, there are two places where you can find them. One of them, if you go to the program page on the website, you scroll down to detailed schedule, and then click on the link. What will open is the PDF you see on the right. And at the very top of that file, you have the links to the 7 Zoom rooms that we will be using throughout the conference, throughout the week. Room number 1 is the main room. That's the room we are using right now. And that is the room that will be used for all the plenary session. So if we say a specific talk will be in the main room, that's room number 1. Those links will not change throughout the entire week, or at least we hope that we don't need to change them. Another place you can find those links is in one of the pinned messages on the general channel in the Slack workspace for the conference, which you all should be on. If you're not on, just let me know and we will quickly add you. Most of the channels on the Slack workspace are for Q&A for specific sessions, but 3 of them are not like that. They have a different flavor. One of them is Hello, my name is. That is a channel dedicated for introducing yourself. If you want to introduce your name, where you are at, what are you interested in, what are you working on, please do it in this channel, Hello, my name is, and do not do it in the general channel. And so far that has been working very well. Another channel is the job ad board. If you are on a job search committee, you want to advertise that job search for students, postdoc, faculty, or anything else related to the science of TESS, you can use that channel. And another channel we have is the TOI help desk, where the TOI team will answer any and all questions you have about TOIs. That's about the links to the Zoom rooms. Posters. There are a few ways you can view the posters. One of them is you go to the poster tab or the poster page on the conference website. Then you can see the links to the posters and links to the abstracts, which are also on the conference website. Another one is Zenodo, where we have what is called Zenodo community for this conference. And you can see that right now we have 191 posters there. And this poster repository is searchable by keywords. Like if you click stellar flares, you'll find posters about stellar flares. Or you can look for an author's name, and you can see the posters that author is on. And another place where the posters are at is at the GatherTown space. We had a problem with the GatherTown space yesterday in the reception, but it was fixed yesterday, and it should work today. This is the main room in GatherTown, and you can see it has entrances to 9 poster halls, each of them containing up to 24 posters. And each of those 3 panels or small boards, you walk up to them, click on the X, you wait a few seconds, and what will open is this Google spreadsheet file containing the list of posters. Poster ID is the hall name, meaning the room name or room number, dot poster number. So 3.21 is located at hall number 3, poster number 21. And there are several other rooms here. You can explore it, and maybe at the very end of the session, I will walk you through all the fun stuff we can have in GatherTown. And GatherTown is a tool also for social interaction, not only for posters. It will remain open until a week after the conference ends. Another online tool we are using is the YouTube channel, where we will put the recorded talks from this week. And you can also find the long version of the talks given by all the panelists in the 5 panels that we will have this week. And last but not least is social media. We have the conference has a Twitter account, so we can tweet at us and use the hashtag TESSCon2. So that is it for the logistics. I hope we all have a fun, productive week. And I'll hand it over to Dave Latham, who will be chairing the first session.
Okay, thank you, Avi. Here's the schedule for the first presentations in this session. There's 3 talks on the status and planning for the future of the mission. There are 25-minute talks for the invited talks and 15 minutes for the contributed talks. We're right on schedule to start at 9:10. So George, I'm going to introduce you and let you take over and talk about the status of the mission and what's going to happen in the future. Stop sharing.
Thank you, Dave. Can everyone hear me?
Sounds good.
Okay, and I'll start with this. Okay, well, it's really hard to believe that it's only been 3 years since we commenced the science program with TESS, and I'll go through and mention a few of the highlights in a more general way, and also some of the ideas that we were thinking of for the upcoming years, and in fact the next extended mission that we envision that TESS will actually be able to carry out. This is a familiar picture to many of us. It's TESS looking at the south ecliptic pole, and it gives you a very good idea of the breadth of the 2,300 square degrees that TESS is able to bring in at one moment. And we've had 10-minute full frame images. Now we're having ideas about how to extend that in the future. 300 million stars and galaxies have been observed over the last 4 years of the mission, the last 3 years of the mission. And we've also had a lot of success using the 20-second sub-images for about 10 to the 4 stars to date. There's no proprietary period, and that's, of course, been one of the major strengths of the TESS mission. And as a result, TESS is enabling a very high rate of discovery papers. And there are 2 reasons that this has been a major strength of the mission. One is that, as I said, the data has no proprietary period, but it's also the fact that the cameras themselves are really exquisite photometers. The precision that we're achieving is about 100 times better than what you can obtain on the ground. The performance of the instruments in the spacecraft has been absolutely superb, far better than what we actually expected that it would have. And altogether, we can explore at will 300 million stars and galaxies. In terms of what's actually occurred so far in the publication record for TESS, that's another wonderful aspect of the mission. This is a plot that shows the peer-reviewed publications by year. Here we are in 2021, and there's been 217 thus far. And at the rate at which it's going, that'll be about 1 paper per day in this year. And if you compare TESS to other NASA missions that have been flying for quite a few times, this is publication rate per year versus years following launch, and that's where TESS falls within this. So TESS is definitely hitting above its weight in terms of the cost for the missions that we're actually, in some sense, being compared to. The peer-reviewed publications by topic have actually changed a little bit as the mission has gone on. Initially, it was very heavily oriented toward exoplanet specific publications, and now there's quite a bit more in the way of general astrophysics. And that's certainly something that was not fully anticipated or expected, but yet it's been very beneficial for the community as a whole, because TESS can definitely do 2 things at once, and the mission has been very successful in demonstrating that. Another idea that is very clear from the open data policy is the requests that have been made by the community as a whole for the data itself that has been in the MAST archive at Space Telescope Institute. This slide shows some of the download records just in the last 3 months. And altogether, there's been a 1.5 million quick look pipeline light curves from a lot of different addresses. And it's very clear that we were reaching a level of about a petabyte of test data per year that's actually being downloaded. So it's very gratifying to all of us who've worked so hard on the mission that we're able to provide this in an open way to the entire community. This is one of the types of data forms that are in the MAST archive. This is a photometry of 10 million stars from the first 2 years, the TESS full frame images. This is a high-level science product. And one of the things that you can see from this is that the precision that we're getting versus test magnitude is at the 10 parts per million level based on the envelope of the photometry that's actually illustrated in this paper that was headed by Chelsea Wong. The follow-up program has been a really great success. This has been orchestrated through the TFOP organization, with now more than 500 members being part of this. And you can see from these little flags the number of people who are actually participating in the three aspects of that: photometry, imaging, and spectroscopy. And there's going to be another talk on this a little bit later this morning by Karen Collins, and learn about how these ground-based light curves can also be used to supplement TESS' data itself. It's also a real pleasure to mention that we've met our level 1 requirements for mass measurements of the from the mission. This is a slide that Sam Quinn put together. So far, the goal was at least 50 measured masses for less than 4 Earth radius test planets. And we've exceeded that already. And so it looks like we're well on our way to doubling that number in the coming year. Many new masses of small planets are in process, despite all of the problems that ground-based observers have had with COVID. And then there's many new masses from the prime and successive extended missions that will actually be filling in this diagram, and that diminishment in the slope is a temporary effect, I'm quite sure. This is another thing that you'll be hearing from this morning is a talk from Natalia Guerrero that actually shows that we've achieved a large number of TESS objects of interest, and of the 4,300 plus that we've seen, there's 3,600 of those that are planet candidates, and about 800 of these are planet candidates that have a radius of less than 4 RE. So this is another a milestone in the performance of the mission that I think we can all be proud of. Continuing on, there's a new faint star search that's going on at with the Quick Look pipeline, and this is being headed by Michelle Kunmoto and Tansu Dalen and others. And so far, this has resulted in 1,600 new TESS objects interest, and there are many more thousands that are expected. So I think as a milestone, we can look forward to perhaps more than 10,000 TOIs by the time we have another TESS Science Conference, hopefully in 2 years' time. The other thing is that we've been able to address many astrophysical topics with TESS over the past 3 years. Here's a tabulation of some of the things that have been looked at. And one thing that's been particularly intriguing is the effective way in which difference imaging has been used with the TESS images. This is a panorama by Deb Woods that shows an image with all the stars and other objects present on the left, and then the difference imaging shows a greatly diminished portion. These little shadow patterns are due to differential stellar aberration, and then when the object is actually looked at, that was of interest with a step and stare process, then you're left with this one isolated moving object. And another one of Deb's slides that I think is really interesting shows the spatial density of asteroids that TESS has observed. And there's 4,300 unique objects that have been reported to the Minor Planet Center. And this is something that's going on. And the gap that you see in the data here is just the fact that TESS, at the time this figure was made, had not yet made these observations. And of course, when we do in the coming months look at the ecliptic plane, this gap here will also be filled in. So I'm sure the numbers that we're going to be dealing with is going to be well over 100,000. And it's gratifying to see TESS used in a way that we did not fully envision as a source of primary science at the beginning. In another area also that has been very effective These are observations of trans-Neptunian objects in the outer solar system, Sedna, Kaiju, and this other object, TG422. These are images that have been compiled using ship and stack methods. Matt Holman, Matt Payne, and Anders Paul have contributed greatly to this work, as has Melina Rice and Greg Laughlin. And I think we'll be hearing from Melina later in the conference. For the extended mission going forward, I'll spend a few minutes talking about that. This will commence next October, and it'll extend until October of 2025 to bring us into sync with the NASA fiscal year. There's a growing number at MAST of high-level science products that have been put together by a large number of people. This column right here shows the number of objects that are actually part of these lists. And one in particular that I'll spend a little more time talking about are the TICA FFIs that Michael Fastenau and Chris Burke have been leading an effort for, which have already produced information for 60 million objects in 14 sectors. And then in the way that this will actually be used, it has relevance to the extended mission as we go forward. We're going to make some modifications in the way that TESS actually operates. This panel here actually shows the concept for operations that we're currently following, where we have 2 downlink sessions near perigee in Ka band, and then a number of S-band contacts that are primarily used for housekeeping data for the satellite. In the extended mission that's coming up, we're going to keep one of those contacts at perigee, but the other one's going to be moved out to apogee. And as a result, the information that we'll be able to gather from TESS will be increased without increasing the number of contacts that we have to use for the Deep Space Network, which is always at a premium. We're also moving to 200-second FFIs during this period of time. And then we'll also be able to bring the data down more promptly, and that will mean that the latency will be decreased down to 7 days. Now, one of the things that we think we can actually do with this is the data flow within the POC and SOC that we envision for EM2. And what I've shown here focuses on the FFIs that arise from TICA. When the data comes down through the DSN, these marks in black that I put on here are roughly the times that these different processing steps require. In this initial stage, that actually results in full frame image, pixel calibrated images with astrometry. That process should be reduced to somewhere in the range of 2 to 3 days. For the actual production of light curves by the quick look pipeline, these steps are involved here, and we expect to be able to work through this in somewhere in the range of 11 to 12 days. So this will be dramatically faster than what we've been able to do with the mission today. Now, another thing that's happened is that the awareness of TESS's value to James Webb for targets has been fully realized in the initial cycle 1 listings that have been put together. And so the gold stars in this are TESS discovered exoplanets, of which 25 of the 68 transiting exoplanets that are going to be targeted in cycle 1 originated with TESS. The GI program continues to be extremely successful. There's the review processes have been able to assign not only time from TESS, but also time on other NASA missions, and that's expected to occur in the future. And in cycle 5, 6, and 7, we're going to anticipate that the same level of target and funding allocations will be obtained as was the case for the 1, 2 that we've done so far. Now, in just a couple of minutes, I'd like to talk a little bit about sort of a new concept that we've been discussing for what, for lack of a better name, is called TESS L5. And this is a way to utilize a flight spare that we have from TESS initially that can actually be launched on a small satellite. And then the idea is that it would go to the Earth Sun L5 location and could actually provide full frame images at a 200-second cadence for every pixel in every CCD. And in order to bring this information from that distance, which is about 1 AU away, it's about 500 light seconds as a baseline, it's going to require about a 6 megabit per second optical lasercon link. And I'll talk about that again in a little bit. The sensitivity with full frame image stacking and the coincident operations from the overlapped observations will actually allow TESS to go even deeper and have greater sensitivity than the combination of TESS and TESS L5 than would be the case before. And the science that we would be able to explore even more extensively from this would be continuing time domain astronomy, especially in solar system objects. There will be a great benefit from this because you'll be able to utilize parallax measurements to determine at any given time where the objects that are observed actually are. And since it's expected that TESS may be able to detect of order 500 additional TNOs, that's another new thing. And of course, when we look at these signals that we'll be able to obtain from this object, which is well away from the Earth, topics like diffuse extragalactic light may be possible. And there's also technosignatures from the times that we would be able to look in the ecliptic plane that TESS can actually search to in collaboration with the SETI initiatives. The way this would actually work, and I'll show it in this little diagram. This is TESS orbiting the Earth in its 13.7 day orbit, and the fields of view of its 4 cameras. When you bring in TESS at L5, it will in fact be at L5. And then the baseline of 500 light seconds would be the way that the data would come back over a laser comm in order to achieve that. And its field of view of its single camera would be identical to that of the 4 cameras that are in TESS. And then as you actually step around the sky, one of the things that you can achieve is you can look in coincidence with any of the other 4 cameras as needed, and then that can be carried out during the coincident mission. One of the other things is that since TESS L5 is actually doing its communication by laser comm to the daytime side of the Earth, the systems that will actually be used for bringing the data down could actually be used for observational astronomy at night. And in fact, this is what this mission would require. The flight spare camera actually exists already. The laser comm system would operate at 8 megabits per second and would require a small onboard telescope with a narrow field. And the robotic network would have 1 meter telescopes associated with them. And these would be used during the daytime for only about an hour per day by TESS as the Earth rotates through the field of view of each of the as the Earth rotates here, different of the 6 or 8 ground-based telescopes would be available for transmission from TESS. And one of the other things that you'd obtain from this is that since TESS will be looking at the sunlit side of the Earth in its field of view, that for at least some of the pointings, that means that you would be able to look at sunlit near Earth objects as they approach Earth from the direction of the sun, which is extremely difficult for any other methods to detect these threatening objects. Okay, now I'd like to just shift back and summarize. These are the timelines that we have for the coming decade with TESS. This is where we are in the current extended mission here in August of 2021. When we move to the next extended mission, which will cover this 3-year period here, eROSITA and CHEOPS will hopefully continue to operate well. There's been a great deal of very exciting results that have come from the CHEOPS mission in collaboration with TESS. Webb will be fully operating during its design mission. LIGO will be operating, and the Rubin telescope will have commenced its 10-year survey, and TESS and Rubin should operate very well in conjunction because the Rubin telescope works extremely well for objects that are that are fainter than 17th magnitude, and of course TESS can operate for transient events that are brighter than that. So the two are very complementary. The EELTs will start to come online, and hopefully we'll have the Roman telescope coming in the 2025-26 period. So for this next extended mission, we would be transitioning into the era in which Plato and Ariel and the Roman telescope will actually be major contributors to searches for exoplanets, as well as other types of astrophysics that TESS has performed so well. And all during this period of time, there's an opportunity for making coordinated observations with TESS and Hubble, Chandra, and NICER is another mission that the ability of TESS to look at flaring objects will be important. SWIFT is still operating in XMM, and there will be coordination with those missions. So as we move out to this next extended mission, here are some of the takeaways that I'd like to leave you with. And hopefully, since we have been invited for the 2022 Astrophysics Senior Review for our extension to 2025, we'll be at the time that we have our next TESS science conference, then we'll be able to report even more of the exciting results that the community has brought forward to us. So thank you.
That's great, George. We have several questions. David Wilson asks, will the new downlink at apogee result in a gap in the TESS observations?
There actually will be almost an additional day longer of observations. There will in fact be 2 gaps, but they'll be shorter than what we currently have, because with the operating mode currently at what we call LEHO, there's not only the transmission time of something like 5 hours, but there's a 1-day gap between LEHO 1 and LEHO 2, and then there's another 5 hours. So with this operation, with this operating mode, there will no longer be that gap, and so it should provide possibly as much as an additional day of observations per orbit.
James Jackman asks, will the availability of the 200-second cadence FFIs result in a change to the number of available 2-minute and 20-second cadence targets that GIs can propose for?
I think there's a possibility that there could be changes that will take place. We would not envision that there would be any diminishment in the 20-second targets. Roland's going to talk about this a little bit in his talk that's just coming up now. But I would imagine that there will be classes of observations for which the 200-second, that is 3 minutes and 20 seconds, would be fully satisfactory for objects that previously have received a 2-minute cadence assignment.
And one final question from Ben Monte. Thanks for the clear overview, exclamation mark. Would the TESS L5 telescope have the same bandpass as TESS or operate with a different filter to gain color information?
At present, we're not envisioning making any modifications to the camera itself. It's a piece of flight hardware, and I don't think that we would make major modifications. There's certainly not going to be anything like a filter wheel. Whether you would change and put a filter on it that would modify the pass band from 0.6 of a micron to 1.1 micron is certainly something that we could look at. But I think the whole idea of having coincident observations is one of the major strengths that this geometry would provide for us.
Well, thanks again, George. Very impressive accomplishments so far, and looks like we got years ahead of us. The next talk is going to be by the Deputy PI, Roland Vanderspek. Take it away, Roland.
I'm taking. I'll ask the standard question. Can you hear me and see me? No response, that means I'm good. Good morning, all. I'm Roland Vanderspek. I'm going to tell you a little bit about the status of the TESS observations and operations. I'll break this talk into 3 parts. We'll talk about spacecraft and instrument status first, then talk about target selection, and finally, a little discussion about observation pointings, not only in the past, but in possible extended mission pointings. Before I go on, I'd just like to point out that Eric Jensen has a, Eric Jensen has a great website at Swarthmore, which uses the HIPS library to do much better visualizations than I did when I put together this TESS Death Star. It's worth looking at. So we'll start with the spacecraft. Frankly, this is easy. The spacecraft and the instruments are all working really well. There's really been no change in their performance since the beginning of the mission, which is really nice to be able to say after 3 years. The cameras are healthy, focus and temperature are stable. We've had reports of a few hundred bad pixels, but this is a very small fraction of the total 70 million pixels in the TESS mission. The spacecraft pointing stability continues to be very good. We meet our requirements, we exceed our requirements with good margins, but that doesn't mean that we won't try to make improvements. One example is here, on the upper right, you'll see a plot of the spacecraft stability around its 3 primary axes as a function of time during the first orbit of sector 26, which was the last orbit where the spacecraft was pointed very far north. And you'll see a lot of hash around the Y and Z axes. We found that that was correlated with a heater that was cycling on one of the spacecraft panels. And we tweaked parameters so that it didn't do that. And in sector 40, the performance is significantly better. You won't see that hash. The data downlink is consistent. DSN has been very good about upgrading its hardware and software to provide really consistent and reliable contacts. I think it's a credit to them that no science data at all has been lost during the entire mission. TESS operations, the day-to-day workings of orbit planning, data collection, data processing is in a steady rhythm. It's all quite routine. COVID didn't impact us that much. First off, the various groups, the POC at MIT, the SPOC at Ames, MAST at SDSCI, we're all remote anyway. Internal operations at the POC, for example, using Zoom was not a problem. We all got used to it very quickly. We're in sector 41 now. We're collecting 20,000 targets at 2-minute cadence and about 1,300 targets at 20-second cadence. We're doing 10-minute FFIs now. And sector 42 is the first ecliptic observation. The data processing pipelines have also been extremely reliable. The SPOC process data are delivered to MAST. They get to SPOC and come back to MIT and go to MAST within 3 to 4 weeks of their downlink to the ground. John Jenkins has a poster that describes this. The TICA calibrated FFIs that George just mentioned are a high-level science product that are sent to MAST within about a week of receipt on the ground. So target selection. As you know, 2-minute and 20-second targets for each sector are extracted from a candidate target list. They are sorted by priority and location on the CCD. And the 3 main CTLs, Exoplanet, GI, and DDT, are each allocated a certain fraction of about 18,000 science targets we observe per sector. The gory details of this are in Fosnau's paper, Michael Fosnau's paper, which should hit archives soon. In the prime mission, the emphasis of the targets was the exoplanet CTL. So 80% of the targets went to exoplanets. In the first extended mission, the emphasis went to the GI program. So they received 80% of the targets. And you can see that this is worked out. This plot on the right is the fraction of total science targets observed by CTL over the first 3 years of the mission. Blue is exoplanet, red is GI, green is DDT. And you can see that in the first 2 years, exoplanets did indeed receive the lion's share, but GI is getting the emphasis now in year 3. In the extended mission, we're still talking about this. I don't see any reason to tweak the allocations, the relative allocations, but as one of the questioners mentioned, and as George responded, there may be discussions of reducing the total number of 2-minute targets because we'll be doing FFIs at 200 seconds. We'll discuss this in the coming months in the preparations for the senior review. The 20-second targets will probably, I would guess they would go up from there, 1,300 or so right now. In extended mission 1, almost all the GI targets that were requested were observed. It's over 90%. This plot on the lower right is a fraction of the possible targets from each CTL that are in the field of view that actually made it onto the target list. The exoplanet numbers are generally low in this metric because the exoplanet CTL is really big. But you can see that it's actually over 95% of the GI targets are selected, which means it's not oversubscribed, it's not undersubscribed, it's just right subscribed. Well done, Tom Barkley. In year 3, we observed about 60% of the 20-second targets from GI. In year 4, we realized that we could up the total number of 20-second targets without affecting operations. So we kicked that up starting in sector 40, and now we're observing essentially 100% of the 20-second targets given to us by GI. But speaking of targets, there's a new version of the TESS input catalog, and this is something you should be aware of, TIC version 8.2. In 8.2, the dispositions of about 33 million stars in TIC 8.1 have been updated based on cross-matching between Gaia and 2MASS. The bulk of these are either duplicates or artifacts. Artifacts are images, spurious images in 2MASS plates that were identified as incorrectly as stars. Duplicates can either be 1 star in 2MASS actually turned out to be 2 stars in Gaia, or it can be 1 2MASS star and 1 Gaia star were actually the same star and that had to be improved. This affects about 0.5 to 1% of the TESS targets, and it can impact crowding estimates and measured stellar fluxes. Now, 8.2 is being used in data processing at SPOC, starting with sector 38, and it will be live at MAST soon. So you should look for documentation at MAST, on archive, and in the TESS data release notes describing TIC 8.2 and the impact on photometry. There may also be an entry at the GI office advising you how to handle targets that have been declared duplicates. So let's talk pointings now. As you know, the standard approach for TESS is to observe an observing sector for 27 days, then shift the field by 27, roughly 27 degrees, and continue this process. So in year 1, we used this method to map the southern hemisphere for sectors 1 through 13. This is the same view in ecliptic coordinates. In year 2, we did sectors 14 through 26 in the north. So covered as much of the northern hemisphere as we dare. Now there's this gap here where we lifted the fields of view about 30 degrees further north to avoid contamination of cameras 1 and 2 with excessive amounts of scattered light. This is due to the fact that the Earth is near the camera's field of view at orbit apogee. So the scattered light dwells there for about a week per orbit, which is not good for exoplanet science. Year 3 was the beginning of the first extended mission. The goal of the first extended mission was to reobserve as much of the sky as possible, to look for longer period planets and to improve ephemerides. We started the 10-minute FFI cadence there. And one of the goals was also to start observing the ecliptic, since we'd mapped the 2 hemispheres to the extent we could. So year 3 was simply a reobservation of the southern ecliptic hemisphere. Now, because of the way the orbit works, the gaps between sectors that you saw in year 1 were pretty much covered up by these observations in year 3. There are very few gaps in the southern hemisphere. Year 4 is now going to be a combination of northern and ecliptic observations. We started with 2 north-shifted sectors, 40 and 41. Then starting in late August, we'll do 5 ecliptic sectors, and then we'll do as much north as we can before the end of extended mission 1, sorry. Again, we did have to shift 40, 41, 52, and 53 north to avoid the scattered light issue in cameras 1 and 2. But now let's take a little bit of time and look at the ecliptics a little bit more closely. I overlaid the sky onto these plots. And the thing that pops out is the K2 fields. It turns out that we've arranged the ecliptic observations to cover 15 of the 20 K2 fields. So they'll be observed during sectors 42 through 46. Now, the way that the ecliptic observations work is that we basically lay the spacecraft on its side. The cameras are now splayed parallel to the ecliptic. And in sector 42, this is what it looks like. Typically, we would shift the fields by 27 degrees between sectors just to keep up with the motion of the sun, or the Earth around the sun. But instead, we're adding an extra 10 degrees to sort of stretch out the field. We do this for sectors 43, 44, 45, 46. And in that way, we can cover 240 degrees of the ecliptic. So 2/3 of the ecliptic will be covered by these observations. Another byproduct of the ecliptic observations is that certain parts of the ecliptic will be observed multiple times. So here, for example, these sectors, this region will be covered in 1 sector, this in 2, this stripe with 3 sectors. So essentially, effectively 3 months of observations there, and so on as you go through. Another thing we did with ecliptic observations is to bias the fields east. There are no restrictions on exactly how we bias the spacecraft when we're pointing in the ecliptic. So what we've decided to do is put camera 1 34 degrees away from antisolar, east of antisolar at sector start. And over the course of that sector, the Earth will have moved around the sun, so it will be about 6 degrees from antisolar at the end of the sector. But the key is that the edge of camera 4 is about 4 hours east of antisolar at the end of sector 42, which means you have ample opportunity to follow up stars. Typically, the stars are about half an hour or an hour east of, the best stars are about an hour east of antisolar at the end of a sector. For sector 43, the situation gets better as we push further east, so that in sector 46, the edge of camera 4 is 6 hours east of antisolar at the end of sector 46. Because of the way the spacecraft is laid out, the edge of camera 4 at the beginning of sector 46 is only 60 degrees from the sun, but we have a sunshade to take care of that. The scattered light is going to be interesting in the ecliptic. The ecliptic is the home to the moon, the Earth, the planets. And so we had to balance our pointing strategy around that. At upper left, you see one of our standard plots where we plot the angle of the Earth and the moon from the bore sights of each of the 4 cameras. The Earth is the thick lines and the moon is the thin lines. And this is over all of sector 42. And you can see at the beginning of sector 42, the moon is just going to be wandering through all 4 cameras, adding to your background. And at the very end, the Earth will show up in camera 4. This is probably the worst case. As we move on, the maps look more like this, where there's hardly any interference at all. So now we'll come to extended mission 2. The goals that we're proposing for extended mission 2 sky coverage is A, complete the survey of 100% of the sky, no more gaps. And 2, to cover as much of the sky as possible using the 200-second FFIs that George mentioned. The survey strategy that we're thinking at this time will mimic what we did in the prime mission and the first extended mission: Northern Hemisphere, Southern Hemisphere, finish the ecliptic. And I've put together one possible pointing plan here. We'll make some minor tweaks to the pointing to make sure that we cover the gap at the north and south ecliptic poles and the CCD gaps that are at plus or minus 18 degrees ecliptic latitude. So this is a proposal for year 5, finish the north, which we had started in year 4, and just start doing a southern observation. In year 6, finish the south. We'll do an ecliptic observation that will now cover that gap that we have in year 4, and then restart the north. And in year 7, we'll do the north, and we'll have some sectors at the end. We can restart the south. Now you'll notice that the fields that have been lifted north to avoid scattered light are in a different location. That's because the orbit of TESS has precessed to the point that this region is shifted by about 90 degrees. But it's basically between year 5 and year 7. It's zooming from where it was to where you see there. So this will give us a little bit of pause here. One of the trade-offs that we'll be looking at is whether it will be better from a scattered light standpoint to do the ecliptic observations in year 7 and then push the northern hemisphere stuff to year 6, because those sectors where the yellow ovals are in pretty bad shape regardless. The Earth will have moved from being between cameras 1 and 2 to being between cameras 2 and 3. So yeah, but that's all part of the process that we'll be following in the preparation of the senior review in the coming months. So I'll summarize by saying the spacecraft is in great shape. Flight operations are running smoothly. We're preparing for extended mission 2. And we're just really looking forward to you guys doing even more awesome science with the data that we can provide for you. Thanks very much.
Oh boy, a lot of really interesting details there for the upcoming years and the new way you divide up the targets. Great stuff. And you've left a lot of time
Have I really?
questions. And Eric Jensen has left some links in the TESS mission channel on the Slack site, so you can go find out about his tools.
Yeah, go look at that. The visualization that he did is really pretty. I wanted to try to use HIPS to do these things, but I'm not smart enough to do that. But he is, and it's a lot of fun to work with.
And Jennifer Burt asked the question, which actually I had in mind as well. Well, first of all, she said, great talk.
Thanks, Jen.
How many years of extended missions would be necessary for the moon to move enough so that TESS could eventually cover the whole area that's currently obstructed? looks like you're covering it in year 6. Is that true?
Yeah, it's more a question of quality, not quantity. You know, we can observe the whole sky, but you'll be killed by the Earth. It's mostly Earth, Jen, for a week at a time during some of the bad sectors. So the cycle, it turns out that bad area, the yellow oval I was pointing at, it sort of dwells where it is now for about 4 years, then moves quickly over to the antipodal spot in about 4 years. So it's year 7 is right in the middle of that transfer. Then it sits there for a while, and then it comes back to the beginning. So there's this cycle, and we can just try to fill in the gaps as that bad region moves around.
And there was a question by Carl Stapelfeld after George's talk that I think you might be able to handle. It's about the downlink strategy that puts you with a contact at apogee.
Mm-hmm.
And are you worried about adverse effects on the light curves because of, say, thermal disturbances or something like that?
Well, I'm not the one. I'm not worried. Others might have a different opinion. Basically, we're going to rotate the spacecraft to point at the Earth for 5 hours for the downlink, and then we'll spin it back and start observing again. There will be a thermal pulse. We'll be further from the Earth, so that impact will be lower, but most of the impact is the sun being moved from one side of the instrument to the other. There will be a thermal pulse, just like there is at the beginning of every orbit. And one will, if we follow this, then one will have to adapt to it. The good news is, though, that you won't have a momentum dump in the middle of the orbit anymore, because that'll get absorbed into that Ka band dump. And as George mentioned, because we're not doing 2 contacts at perigee, we'll have an extra day of observations at perigee. But yes, there will be an impact. No, I'm not too worried about it.
Are you worried about redundancy? Because you won't have am I right to say you won't have as much redundancy on the downloaded data, and you're really relying on the DSN to be super reliable?
Well, right now, Dave, we're doing sort of belts and suspenders. We have 2 downlinks, and we make sure that the onboard solid state recorder isn't more than half full. So we never get it to half full, and we give it 2 chances to downlink. Despite that, we have procedures in place. If we do manage to miss both contacts twice, there's a way for us to call out data either that's already been downlinked, or data then, ultimately the worst case is figuring out which data we're going to sacrifice. But frankly, DSN's been very reliable. We do have 1 backup. We have 2 contacts to get the data down. 5 hours is enough to get the whole spacecraft memory to the ground. So it's less than what we have, but it's certainly adequate. Certainly,
yeah, sounds like it is. Well, great talk, Roland. Thanks again.
Thank you, Dave.
And we're going to move on to Natalia, a 15-minute talk. So I'll give you a warning 3 minutes before the 15 minutes are up, so that you'll know it's about time for questions. And Natalia is going to tell us all about TOIs. I'm looking forward to this one.
All right, so let's share my screen.
Looks good.
Great. All right. Hi, everyone. My name is Natalia Guerrero. I am the TESS Objects of Interest Manager at the TESS Science Office, and I'm excited to say I'm actually in the TESS Science Office for this talk, which is a big deal after being not at MIT for about 15 months. So I'd like to share about the progress that we have made in creating this TESS Objects of Interest catalog since the mission first began in 2018, and a little bit more about what it's able to do for the community. So in essence, the TESS Object of Interest catalog is this system that works really well for enabling others to find and explore various phase spaces of interesting exoplanets. So what have we done so far in terms of TOIs since the start of the Prime mission? So here I have a period radius plot that's empty. This was right at the beginning of September of 2018, right before we started releasing the first TOIs. And I will run this forward. And so this is in the first year. And I'll pause it here because this is where we were at. Whoa, there we go. I will pause it there because that is where we were at in the first year of TESS, which was the first TESS Science Conference. And then running it forward, we continue on being on the second year of TESS data in the Northern Hemisphere and continuing on in the extended mission. So this table is definitely filling up with dots for each TOI. And especially in these last 2 months, I wanted to highlight these in particular because this is when the faint star search led by Michelle Konemoto released over 1,000 TOIs into the catalog. So I mentioned her, this is a team of a lot of people that makes the TESS Objects of Interest catalog possible, that contribute to the Quick Look pipeline, that contribute to the TEV online platform, both for vetting and hosting the catalog. There's a lot of people whose work goes into making this enormous effort possible. And on top of that, we also have our steering committee and our vetting team. The vetters are an amazing, dedicated group of people that have been contributing since the start of the mission. I think we're up to over 100,000 individual labels on given light curves, going from the data to light curves to targets that we think are interesting for the community to follow up. So I've highlighted in orange the vetters that contribute the most, both to individual vetting, labeling targets initially, and then also to group vetting, where we come together and assign final dispositions of planet candidate to given targets. So I am really proud of this team and everything that they have accomplished. So I mentioned that we have the system that has been working really well. So George already talked about TOIs with measured mass. And these are just teasers of all of these different types of exoplanet science that are going to be talked about later in the meeting at posters and given talks that all are connected back to the TOI catalog. So community TOIs, Ismael Morales, who was part of the TOI team before, is talking about those contributions, as well as by Planet Hunters. TOI false positives, Catch Karen's presentation. In addition, there's other, starting to dig into exoplanet science, the TOI systems spanning the radius gap, host star properties, the Neptune desert. Catherine Hesse is presenting on that. Habitable zone TOIs and long period TOIs. And this is just skimming the surface of some of the biggest topics that all are fed by the catalog. So I'll just show a couple of plots just illustrating host star properties for the TOIs. So this is an updated version of a plot that is in the TOI catalog mission paper that came out earlier this year. So here we have a color magnitude diagram with the Gaia bands on the x-axis and the Gaia absolute magnitude on the y-axis. And this, you can see that the blue dots, which are the TOIs that are active, follow the main sequence. And then the false positives, which are the yellow X's, we have some that also follow the main sequence, but also go into the evolved star regime. And these dots are TIC8 stars that follow more of the main sequence. And so TOIs fall all along the main sequence. And so this is starting to hopefully prompt interesting questions about where and why these targets show up where they do. Also going back to the period radius plot, now showing this with the TOIs with period on the x-axis and radius on the y-axis. And I've scaled the TOI color here to scale with the stellar temperature. So you can see that there are stars that are small, cool stars that we have small exoplanets around those. And then also we have large exoplanets around small, cool stars. And also around hotter stars, we have hotter planets, but this is starting to show that we are exploring different phase spaces of stellar hosts for given stars. And so giving TOI as a broader context, this is a map of transiting planets from other surveys. You can see up here, this is the distinctive Kepler blob that was observed in year 2 and that we're going to observe again in year 4. And then here along the ecliptic, it's notable, you can definitely see some of the K2 fields here as well. And so I'm really excited, and a lot of us are really excited about reobserving those in the next few months. So in year one, TESS covered the entire most of the southern hemisphere. And so I wanted to flash back to the first TESS Science Conference again, where we only had 900 POIs, and I don't think even just barely 24 had been published. And now that those numbers are way higher, we've quadrupled practically the number of TOIs we have. So year two, again, filling up more of the sky. And then with year three, we again return to the southern hemisphere and then add more TOIs to both the north and the south with the reprocessing we've done, and especially with the faint star search. Leading us to this number, this was as of a few weeks ago. I think now the number is up to 4,400. So the TOI catalog is continuing to grow. We're adding more of these exoplanet catalogs, exoplanet candidates to the catalog, learning about false positives, learning about long period exoplanets. One interesting thing I've found is now that we have more data from year three, sometimes we were able to get second transits for targets that we previously only had a single transit for. We're able to refine ephemerides for targets that we've made repeated observations for. And overall, we're continuing to explore and learn more about all of the riches for exoplanet science that TESS can provide. So overall, the TOI catalog is this science enabler. It's providing the ability to, for many different avenues of exoplanet discovery around different types of stars, for long period, short period, all sorts of things. And I'm really excited about, I was scrolling through the abstracts and preparing this talk and thinking about, like, these are all the things that have come out of this mission. And I invite you all to continue looking at the talks for these. So I will wrap up there and take any questions.
Wonderful figures. So we have plenty of time for questions. While I wait for people to type their questions into the Slack channel for the TESS mission, I'll ask a question. One of the things that's really interesting as we keep extending the time coverage is getting to longer period planets. What's the longest period planet that you think is validated or is real, as opposed to it's a possible long period planet?
Right. So as you've probably seen, there's some planets on there that are way out. There's like 700 days. That's like the maximum alias. But I think probably the longest period confirmed planet we have is around the 100-day neighborhood, I'm guessing. I think it's in there.
Right. Well, we've been trying to eliminate the aliases, right? Because of the way you get 2 or 3 or a half a dozen visits, you have to figure out what could have happened in between the visits. It's an interesting puzzle. Well, do we have any other questions from the audience? Well, thank you for being very efficient. That's going to leave a little extra time for our break. And that's showing us back at 10:25, where we'll have a session on exoplanets. And we'll move to the Slack channel for exoplanets for the feedback. Oh, we have one more question from James Jackson. Since we have time, I hope you don't mind answering. When a TOI is marked as a false positive, is there an alert or is it marked silently?
Yes. So we go back, and so for the TOI catalog that's hosted on ExoFOP TESS, there's a column there for the TFOP working group disposition. So that's where either false positive or false alarm will be recorded. And so you can use that to filter out targets that have been eliminated as background eclipsing binaries or other false positives.
I think that fits James' category of silent. You have to go looking for it.
Yes.
I wonder, no, there would be too many alerts. You don't want to do that.
If you want more emails,
Well,
you can provide more emails, Dave.
if you're
Yes,
on the
Eric.
SG1 channel now, you can get the alert, but you will get a lot of them.
Just be careful what you ask for. If you get all of the email traffic from the SG1 team, it keeps you busy hitting the delete button after you read it, of course.
Of course.
Last chance for another question. Oh, Siegfried. Is the detection sensitivity for G dwarfs reaching the size of the Earth?
I am not sure.
Well, it's a question of the period, of course. We don't have anything at 1 year. If you take a late G dwarf, it's not quite as long. I think if you want something that's kind of like the Earth in terms of its temperature, you're going to have to accept looking around M dwarfs right now. The popcorn is still popping. Doug Hudgens. If we observed a transit event during the prime mission and then a second, not necessarily consecutive, transit during the extended mission, how well can we deduce the period of the planet?
That's what we were just
You never
talking
know
about.
if you've got 2 or 3 other aliases that are still
Yeah.
valid.
Yeah, the aliasing. So I think there might be a poster or talk later this week by the long period working group. So Deanna Dragomir, Stephen Villanueva are the people to look up for that.
Of course, if it's a big planet and you can get a transit from the ground at the predicted times for the aliases, you may be able to narrow it down that way. But if you want something that's got less than a millimag, 1 part per thousand, that's pretty hard to do reliably from the ground. So you're going to have to get time on CHEOPS or something like that as a follow-up mission. Or TESS L5. Are you going to, George, you're going to be able to point TESS L5 any place you want to?
It'll have the same viewing constraints for the for where you look in the sky with regard to solar panels. That's something that's a detail that's going to be worked out. It'll probably be somewhat broader because it's got a narrower field of view that you'll, and the other thing, of course, that I didn't emphasize is that you don't have any trouble with scattered light from the Earth at all. The Earth will just be a fairly bright star of magnitude -2 viewed from from L5. So it will have a much broader range of possible locations to view without worrying about scattered light. But as far as the solar, satisfying the needs for the solar panels themselves, as well as the requirements of looking at different parts of the sky, it should have a broader viewing angle. But of course, one of the main ideas is to observe in coincidence with TESS itself, so that we would be able to look for transient events with this enormously long temporal and spatial baseline. So I think that's by and large, it will look at one of the fields of one of the other 4 cameras of TESS itself.
Okay, it's time for a break. You got 10 minutes. We'll start promptly at 10:25 Eastern Daylight Time. That's 11 minutes from now.
Great.
Thank you, first 3 speakers, excellent talks. $320 participants.
That's it. I was expecting 900.
The largest number I saw, Dave, was 360. So it was at that number for most of the talks.
Well, people are taking their breaks, I guess.
Well, some people are sleeping in certain parts of the world too.
This chat is being recorded, apparently. I'm going to go together.
What, you don't like to be recorded?
Roland, could you email me how you actually get onto the Slack channels for this, because I didn't get the information straightened out with, or Avi, if you could do it, that would be great. But my MIT certificates seem to get in the way. So,
Yeah, they expired the day before yesterday.
well, some did and some didn't. It's complicated. So.
Yeah, I think Avi has to invite you again, George, but we can make sure that happens.
Okay, thank you very much. That'd be great to be able to do that, Jennifer. Well done, Dave. This was a very nicely run. Was the are there questions in addition to the ones that you relayed to us, or how does that work? Because
We managed to cover every question that
Really?
showed up in
Wow.
the Slack channel. Not always after the talk that mattered, but actually after talk that was relevant. So
Okay, good.
that worked okay.
Avi or Jen, well, another question about the certificates issue. Now, obviously that affects people at MIT, but for people who are outside of MIT, how do they access the Slack channel?
So I believe I can't do it because I'm not based at MIT anymore, but Avi can just upload a list of email addresses, and then folks should get an invite in their email that says, click here to join the TSC2 Slack workspace.
Okay, good. Yeah, that'd be perfect.
Yeah, so folks were added en masse over the last few days, but we can make sure that another invite gets sent to you, George, and hopefully that'll fix the issue.
Okay, thanks.
Sure.
Laetitia, I think I'll stop sharing and you can load up your slides if you'd like.
Yes, okay, thanks.
Gives us a little extra pad in case we have a problem. But we won't have a problem. There they come. Nu2 Lupi, one of my favorite systems.
Sorry, just 1 second. Here they are.
Looks good. So with these 15-minute talks, I'll let you know with the red card for 3 minutes when we should be moving into questions.
Okay.
Let's see, you're in Liège?
Yes, I am in Liège, yeah.
Oh, there it says on the slide.
Can you see me, by the way? Is my webcam working? Oh,
Looks good.
okay, thanks.
Thirty seconds. Welcome back, everybody. For the second session this morning, we have 5 scheduled talks. And then we're going to have an exciting bonus track. The first talk is Laetitia Delrez from Liège, going to talk about CHEOPS observations of Nu2 Lupi. Take it away.
Okay, thank you, Dave, and thanks to the organizers for giving me the opportunity to present some new results from CHEOPS at this conference. So I will start with a quick reminder about CHEOPS, which is shown here on this timeline in the context of past and future space missions related to exoplanet science. So CHEOPS is an ESA small class mission. It was launched in December 2019. And unlike other missions like CORO, Kepler, or TESS, which were designed to detect new transiting exoplanets, CHEOPS is a follow-up mission dedicated to the study of known transiting exoplanets. And to do so, it relies on a 30-centimeter space telescope equipped with a single CCD camera. So you have here a picture of the instrument during its integration at the University of Bern. And this instrument was designed to obtain ultra-high precision photometry of a single star at a time. So the PSF is deliberately defocused so that the photometric measurements are less sensitive to small differences in the response of individual pixels and to small variations in the telescope pointing. And well, for bright stars with a Vmag between 6 and 9, CHEOPS can achieve a photometric precision of about 10 to 20 ppm per 6 hours of integration time, which could technically allow the transit detection of an Earth-sized planet in front of a sun-like star. And for fainter stars with a Vmag between 9 and 12, the typical photometric precision is about 85 ppm per 3 hours of integration time. Now, the CHEOPS science program is very diverse. It's designed around different themes, which are represented here. I won't enter into the details of all these programs, but if you want to know more, I encourage you to attend the CHEOPS Splinter session on Wednesday. And just to say that all of these programs have one main common science goal, which is to investigate the internal structure and composition of exoplanets, especially low-mass planets in the super-Earth to Mini-Neptune regime. And to do so, one first very important piece of information is, of course, a measurement of the bulk density. And there are two main ways by which CHEOPS is contributing to measuring bulk densities for small planets. The first one is by searching for transits of radial velocity planets by monitoring these systems around the predicted transit times. And the second one is by refining the parameters and especially the radii of known transiting exoplanets that were previously detected by ground-based or space-based surveys. And in this context, we are only focusing on bright targets for which radial velocities will get the mass. Now, the bulk density is a first important piece of information, but this is not enough because the interior models show some strong degeneracies, especially in the low mass regime. So we also have to study the atmospheres of these planets. And in this context, CHEOPS is quite uniquely positioned at the crossroads between the detection surveys and the atmospheric follow-up facilities to identify some golden targets and guide their further study. So there are a lot of interesting synergies between CHEOPS and all these missions, especially with TESS, and the results I will present you now are a good illustration of that. And this is about a star named Nu2 Lupi, and as its name suggests, the star is located in the Wolf constellation here in its back. This is a G4 main sequence star at about 15 parsecs, so this is one of the closest Sun-like stars, and as such, it's visible to the naked eye with a Vmag of 5.8. And based on nearly 11 years of HARPS radial velocities, Nu2 Lupi was known to host at least 3 low-mass planets with orbital periods of 11.6, 27.6, and 107.6 days, and minimum masses in the super-Earth to Mini-Neptune regime. It was then observed by TESS during sector 12 of its primary mission, which revealed that the 2 inner planets B and C are actually transiting. And well, multi-transiting systems around bright stars such as this one are really interesting targets for follow-up observations and for comparative exoplanetology studies. So obviously, we pointed CHEOPS at Nu2 Lupi as soon as we could. And we obtained a total of 6 visits targeting transits of the 2 inner planets, so B and C. And our goal was to refine the properties of these planets, especially their radii, but also their ephemerides. And each of these panels shows one visit. And for each visit, you have the row light curve at the top, the detrended one in the middle, and the residuals at the bottom. And for all visits, well, we observed some instrumental noise, which is correlated with the spacecraft roll angle, and this is accounted for by the blue model here. But we also noticed some higher frequency correlated noise, which we modeled using a GP in green, and this noise is actually of stellar origin. So to characterize this stellar signal, we carried out a power spectral density analysis, which is shown here. And the first thing we can notice is the bump of the stellar acoustic modes here with a frequency at maximum power that is consistent with what we expect from the stellar parameters. And the second thing is this characteristic increasing slope towards the lower frequencies, which is associated with stellar granulation. Now, based on Kepler observations, we know that this slope or flicker index is correlated with the stellar mass, stellar radius, and the surface gravity. And you see that our Nu2 Lupi measurement here in red is in very good agreement with the trends observed by Kepler, but it also opens the way to granulation studies for stars that are brighter than the ones covered by Kepler. Now, I would like to come back to the 5th visit that we obtained with CHEOPS. Maybe you don't notice this earlier, but during this visit, we actually detected an unexpected transit-like flux drop of about 500 ppm, which started during the targeted transit of planet C and lasted for the rest of the visit. And this flux drop occurred at 1.3 sigma of an inferior conjunction of planet D based on the radial velocities. And so we actually hit the jackpot and we caught a rare transit of the outer planet D. And this makes Nu2 Lupi D the first long period planet detected to transit a naked eye star. And as such, this is quite a unique object, as you can see on this diagram showing transiting planets as a function of their orbital periods and the Vmag of their host star. So the Nu2 Lupi system clearly stands out, and especially planet D. Now, for the pleasure of the eye, you have here the phase-folded the transit light curve of CHEOPS on the right to be compared with the ones from TESS on the left. Now, if we want to compare the photometric precision between both instruments, well, it makes more sense to use the RMS of the individual light curves because there is a different number of transits in the phase-folded light curves. And so if you look at these numbers here at the bottom, you see that there is about a factor of 5 improvement for CHEOPS for this object. Now, by doing a joint fit of all these data, we achieved a very good precision on the planetary radii, better than 3% for the 2 inner planets, and a bit larger for the outer one, for which we only got 1 partial transit. The 3 planets are shown here in this plot of planetary radius against stellar irradiation, and the background is color-coded as a function of the density of data point, with the famous radius valley here. So you see that planet B is close to the inner edge of the valley, so it's expected to be mostly rocky. And planets C and D are larger, they are well beyond the valley, so that they are likely to be volatile rich. Now, for the Nu2 Lupi planets, we have not only precise radius measurements, but we also have precise mass measurements thanks to the HARPS radial velocities. So we can test this hypothesis by doing some Bayesian internal structure modeling. And these are the results of our analysis, for which we consider the planets to be made of 4 different layers. So first, Niron and sulfur core, then a silicate mantle, a water layer, and a gas envelope made of hydrogen and helium. And these are our results. So for each planet, you have a ternary diagram showing the mass fraction of the metallic core, the rocky mantle, and the water layer. And you also have an illustration showing the corresponding radius fractions for the metallic core and the mantle together in gray, the water envelope in blue, and the gas envelope in magenta. And based on these models, planet B would be a bare core with no gas and a rocky, mostly dry composition, while planet C and D may have retained some small hydrogen and helium envelopes of about 1% in mass for planet C, a bit less for planet D. And they may also have some large water fractions, which may suggest that they spent at least some part of their formation time beyond the ice line. We also carried out some atmospheric evolution modeling to estimate the initial atmospheric mass fractions for the planets. So these plots here show the current atmospheric mass fraction as returned by our internal structure modeling and compared with the initial atmospheric mass fractions returned by our atmospheric evolution calculations. So for planet B, we find that, well, it looks like it completely lost its primary atmosphere, if it had one, at some unknown point in time. So the framework is not able to constrain the initial atmospheric mass fraction for this planet. For planet C and D, on the other end, well, they are sufficiently massive and far away from the star to be only weakly affected by mass loss. So for these 2 planets, the low gas content that is found today by the internal structure modeling would be of primordial origin. So well, if this is true, this means that they didn't reach the critical mass. And so these 2 objects provide the core mass and the gas-to-core ratio for 2 objects in the same system. So they may be an important anchor for formation models of subcritical planets. And finally, to assess the potential for atmospheric characterization of the 3 planets, we use the transmission spectroscopy metric of Kempton et al. And the planets are shown here as a function of their TSM against equilibrium temperature. The size of the symbol is proportional to the effective temperature of the star. And well, you see that based on this metric, the 3 planets are attractive targets for atmospheric follow-up observations. And in particular, planet D is the best target found so far for studying the atmosphere of a mildly radiated small planet around the Sun-like star. So for sure, the system will become a benchmark target for exoplanet characterization in the years to come. And we actually already obtained some time on HST to search for the atmospheric escape of the 3 planets in the stellar Lyman alpha line. And I think I'm running out of time, so I will just leave you with this slide showing some information about the guest observers program, which is open to all the community. There is also a poster about this by Kate Isaac, so if you're interested, please have a look. And that's it. So I will take your questions here or on Slack. Thank you.
Oh, wonderful system. It's what you really dreamed of. 11 years of radial velocity at very high precision and super accurate radius measurements. We have several questions. Jake Clark asks whether he can ask what the gaps are in the CHEOPS data. Will those gaps be present in all the CHEOPS light curves? Oh, interesting question.
So these gaps are due to Earth occultation because CHEOPS is in a low orbit at 700 kilometers. So these are occultations, but depending when you observe a target and where it's located on the sky, these gaps can be shorter or longer. So for some light curves, we have no gaps at all. And for other ones like these ones, they are quite significant.
Right. But if you're lucky, you can get almost continuous light curves.
Yeah.
If you're unlikely, there's bigger holes. Yes. We have another question. Great to see the measurements of mass and radii. Can the Bayesian modeling break the degeneracy between water and hydrogen content?
No. So for our modeling, we assumed 4 layers, but indeed, technically, the data may also be explained by a 3-layer model with only gas and no water at all. So no, we need atmospheric observations to break these degeneracies.
Yes, I agree. Well, great. Thank you again. Wonderful talk. Wonderful system.
Thank you.
And time is up. And so we're going to move on to François Bouchy.
Hello.
And he's going to tell us about ESPRESSO results. Everybody's holding their breath here, François.
Okay. Thank you very much. Let me share my screen. Yes, it's
Yes.
okay. This way. Excellent. Okay. Thank you very much. So thank you for all the organizer for giving me also this opportunity to give you an overview of mass measurement of TESS small size candidates, so many rocky Mini-Neptune exoplanets. Done with the state-of-the-art ESPRESSO spectrograph. So ESPRESSO is in operation at the Coudet lab of ESO-VLT since end of 2018. So just in time for the first release of TESS candidates. So this presentation is made on behalf of ESPRESSO Consortium. It was prepared also with the help of Francesco Pepe, Christophe Lovis, Maria Rosa Zapatero, Baptiste Cavir, and Roland Greaves. So here is a radius versus insolation diagram showing all the 4,400 TESS candidates so far, including the known and validated planet in green, the false positive in red, and the planet candidates in black. So let's remove first the false positive. And our ESPRESSO GTO program is targeting transiting candidates located in this blue region. So it means with the main goals to characterize rocky population up to the habitable zone, and also to explore the rocky sub-Neptune transition within the 50 to 200 times the Earth stellar irradiation. There is also other open time PI program targeting warm Mini-Neptune population with size between 2 and 4 Earth radii and insolation lower than 50 times the Earth. So move this window. Yep. Okay. Here is superimposed the distribution of Kepler planet from Fulton and collaborators 2017, showing the gap between super Earth and sub-Neptune. And the ESPRESSO GTO is probing this transition between rocky and Mini-Neptune population. One can see also here the relatively good agreement between the Kepler and TESS distribution. So here are the 23 exoplanets, part of 11 systems with mass characterized with ESPRESSO these last 5 semesters. And I will give you briefly an overview of their properties. To do that, we will move to the mass radius diagram. So here is an updated version of the revisited mass radius diagram published by John Otegui in 2019, including transiting planet with robust, reliable mass measurement and regularly updated in the DACE platform in Geneva. So there is two colors. The blue, the black dot correspond to masses derived from radial velocity measurement, and the red one correspond to mass derived from TTVs. And here are the 23 exoplanets with mass characterized by ESPRESSO. I will go through all of them rapidly. So it includes the famous P-MEN-C alias TOI 144 planet, a 2 Earth-sized planet with also an eccentric 14 Jupiter mass companion at 5.7 years. K2 111, part of a very old thick disk G2 star, with also an additional non-transiting planet near the 3-to-1 mean motion resonance. The 2 super Earth LHS 1114B and C with Earth-like bulk composition, and also evidence of an additional long period planet. The sub-Neptune TOI 130, including also an additional planet. The characterization also of K2 38B and C, unraveling one of the densest planet known to date, the K2 38B. And also the system include a potential long period planet also. Mass measurement of the 3 planets orbiting the nearby MDRAF L23132, alias TOI 270, including a super Earth and 2 Mini-Neptune. On the amazing multi-planetary system TOI 178, with at least 6 planets forming a chain of Laplace resonances, which will be presented in more detail by Adrien Leleu on Wednesday at the session 5 TESS CHEOPS synergies, if I'm right. More recently, the detection of the lightest planet measured so far by radial velocity, L9859b, alias TOI 175b, with half the mass of Venus, and including also 3 other super Earth. 2 of them are transiting. And this detection recreates the combination of 161 ARPS data point plus 66 ESPRESSO measurement. Very recently, also the famous LTT 1445A, alias TOI 455, was also intensively monitored by ESPRESSO Consortium. And the 84 ESPRESSO measurements revealed 2 super Earth, as well as an additional non-transiting super Earth at a longer period. And this system was also announced this week, is also announced this week by Jennifer Winters, which will make an announcement at the end of this session. This system, so Jennifer also used a completely independent data set from ARPS, IRES, PFS, Maronis, and also a few points from ESPRESSO.
A Mini-Neptune orbiting, so TOI 1231b, here, sorry, which is a slightly eccentric 8 Earth masses object with an orbital period of 11 days. And also recently, we made a new estimation of the mass of the temperate Neptune-sized planet, TOI 1231, which was previously or recently announced by Jennifer Burt, and our ESPRESSO data show a slightly higher semi-amplitude and also a smaller dispersion. So with this increasing number of small size transiting planet paving the mass radius diagram, we can start to do some statistical analysis of planet properties using also multi-parameters. So this is just an example showing here the planet, the impact of the stellar irradiation. Here you can see the distribution of transiting planet with insolation lower than 50 times the Earth, with comparison to insolation larger than 50 times the Earth. And by the way, this sample of low irradiated planet was recently, or let's say significantly extended thanks to the combination of TESS and ESPRESSO measurement. And we can also see that there is a relatively good agreement between the mass or bulk density of planet with low insolation derived from TTVs and derived from radial velocity. On this figure, I wanted to show here so we have in blue the radial velocity semi-amplitude and their corresponding uncertainty of the 23 exoplanets with mass characterized with ESPRESSO. And as you can see, so about half of them have a semi-amplitude lower than 2 meters per second. The typical uncertainty range between from 18 to 48 centimeters per second. In average, it's about 25 centimeters. And one other interesting aspect is that the radial velocity residuals, or the radial velocity jitter, which is added to the modeling, is close to 1 meter per second. So it corresponds to the red point here. So you can see the typical jitter is close to 1 meter per second. And so it's okay, we have good evidence that it comes from stellar variability, but it is presently a clear limit. And our ESPRESSO measurement photon noise is well below this 1 meter per second. So we have clearly a limit which is coming from stellar activity. So there's still room for improvement. And please attend also on Thursday, there is on session 7 data analysis. Michael Crétinier will also address this point, how to deal with this stellar activity limitation. For some, yes, for TOI 175b, the mass measurement allowed to go below, but it requires a huge number of measurements in order to average stellar activity below 1 meter per second. So it's a clear limit. So to conclude, TESS and ESPRESSO contribute to a significant improvement of the mass radius diagram, and it will allow a more detailed multi-parameter statistical analysis of planet properties. There is a relatively good agreement between masses derived from TTVs and from radial velocity, at least for low irradiated planets. Almost an interesting point is that almost all candidates are part of multi-planetary systems with additional signal in radial velocity. So it's really important also to continue the long-term monitoring of this system. Radial velocity jitter is close to 1 meter per second. It's a severe limiting factor. And I would like also to say that to guarantee high radial velocity precision, it requires a continuous effort of monitoring and maintenance of the instrument in order to guarantee the long-term accuracy of instruments like ESPRESSO. Most of these exoplanets will be prime target for atmospheric characterization, but in order to interpret atmospheric properties, we need a good knowledge of the mass of this planet. And I would like to say also that presently we have some, let's say,
unfortunately, a limited number of nights allocated by ISO for mass measurement. We need more time, more telescope time to characterize all these TESS candidates. Thank you very much.
Very impressive, especially that you managed to get ESPRESSO running just in time for the first TOIs to work on. So you had a head start on some of the other next generation spectrographs that are just coming online now. The Americans are a bit behind you with NUID, for example. Maroon X is also showing very good performance. So there's this whole new generation of spectrographs that are being applied to this science. It's wonderful science. Let's see if we have any questions. Yes, we do. Rodrigo Diaz, very nice talk. Yes, I agree. Besides the offset between ESPRESSO pre and post the fiber upgrade velocities, do you see effects in the cross correlation functions or the full width half maxima?
Yeah, I must admit it's not so clear. There is probably a small effect, but it's smaller than on the radial velocity, but it's depend on the target. So it's is related to the spectral type and also the V signer. And by the way, I forget to mention that Rodrigo will also present some ESPRESSO data later on this week.
Were your operations affected by the pandemic? Did you have to be shut down?
Yeah, I must admit, in fact, we realized that during the pandemic period, there were less of, let's say, maintenance on preventive maintenance on the instrument. On this last semester, we had some trouble with, we had some outliers on our data set coming from ADC, atmospheric dispersion corrector issue, and also some instability of the blue detector. So yes, the restricted limit, the restricted team on the Moon 10 also had some consequences on the monitoring and maintenance of the instrument.
One more question, because it's kind of close to my own heart. Jennifer Burt asked, does ESPRESSO currently have a solar telescope, or are there plans to add one in the future?
Yes, so ESPRESSO has no solar telescope, but there is plan. I know that at least Nuno Santos submitted a proposal in order to install a solar telescope on ESPRESSO.
Right. Well, thanks again. Wonderful talk. And we're going to go on to the next talk, which is going to be by Giulia Venturini. Theory. Well, I'm looking forward to this. The origin of the Radius Valley, insights from formation and evolution models. I guess, Julie, you're from Bern, aren't you? You're showing the influence of all the theoretical going on there.
Yes.
Go ahead and share.
Okay, I share already. Can you see?
Yes.
And hear me well? Okay.
Yes, very well. Thank you.
Thank you, Dave, and thanks to the organizers for the opportunity to present today. I will speak about the origin of the Radius Valley, insights from formation and evolution models. And this is work done in collaboration with Octavio Aguilera, Paula Ronco, Jonas Haldeman, and Christophe Mordosini. So we already heard a bit about the Radius Valley. What is this Radius Valley? So since 2017, we know that the occurrence rate of exoplanets with sizes below Neptune follows a bimodal size distribution. The two peaks were confirmed by follow-up studies. And so today we know that for sun-like stars, there is a first peak of exoplanets at about 1.3 to 1.5 F radii. There is a second peak at 2.4 to 2.7 F radii. And the famous Radius Valley, this depletion of exoplanets between 1.7 to 2 F radii for sun-like stars. For M dwarfs is a bit below, between 1.5 and 1.7 F radii. So the first peak are usually referred to as super-Earth planets and second peak as mini-Neptunes. Until now, the models that have been successful to explain the origin of this, the existence of this Radius Valley were pure evolution models. They are the photoevaporation and core power mass loss. And these two models, what they do is that they compute how the planets evolve after formation. So after this dispersal, they take into account how the atmospheres cool and contract after formation, taking into account heat coming from different sources. In the case of photoevaporation, it's heat coming from the radiation of the central star. And in the case of core power mass loss is heat that remains from the formation of the planet from the core. And so including these heat sources and computing how these atmospheres cool and contract, both models can find these two peaks. There are two equilibrium points. So one is for cases where the atmosphere is completely stripped and we end up with first peak planets or stripped cores. Or the second equilibrium point is found for planets that retain 1% approximately by mass of hydrogen helium atmosphere. And this would lead to these sub or mini-Neptunes. And also both models are able to reproduce the two peaks only when the underlying cores are rocky in composition. This is seen here by this silicate curve in the case of photoevaporation, and here in the middle panel in the case of core power mass loss. So both models can predict the two peaks as long as the cores are rocky, and therefore they conclude that most of these planets are water poor and therefore probably form inside the water ice line. But this is actually completely at odds with what formation models find, because this is mainly because of two reasons. First, beyond the water ice line, there is much more solid material, so it's more efficient to form the cores of planets, and we expect that planet formation occurs readily beyond the ice line. And also for planets more massive than 1 Earth mass, type 1 migration is very efficient. So planets that start forming beyond the ice line can easily migrate inwards and end up at short orbital periods where these sub-Neptunes are observed. So from formation perspective, we expect that mini-Neptunes are actually water rich. And this is predicted by many different formation models with very different assumptions of formation by planetesimal accretion or pebble accretion, or even just studying N-body embryo-embryo collisions after this dispersal. So we were very puzzled by this inconsistency between predictions given by pure evolution models and pure formation models. So we decided to tackle this problem with a combined perspective. So doing performing simulations of formation combined with evolution. And we did this in these two works that were published at the end of last year. So our main assumptions in our simulations are the following. We consider planets are formed in protogaseous disks. The disk evolves under the irradiation and photoevaporation of the central star, and also by viscous accretion. And this gaseous disk contains dust that is evolving into pebbles by coagulation, fragmentation, drift, and ice sublimation at the water ice line. And in this disk, we consider the formation of a planet from a moon mass embryo that grows by accreting pebbles and also gas from the protoplanetary disk. So this protoplanet grows in these disks and is also undergoing migration, which typically places planets very close to the disk inner edge. Finally, after the disk is gone, we compute the evolution by photoevaporation during 5 gigayears. So what do we obtain after running our simulations? This is the output of the formation and in terms of formation tracks. So here we see different embryos growing in a disk at different initial locations. And so here is the orbital distance versus mass of the core. And the color bar is the ice mass fraction of the core. So red means that these planets are dry, were completely formed inside the water ice line. The water ice line is initially here and is evolving as the disk evolves. And blue planets are planets that have a lot of water in the core, and so mainly grew beyond the water ice line. And something very distinct that we see in this plot is that the dry cores grow typically much smaller to lower core masses than water-rich cores. And this is also seen later when we study the formation of a full population. So why does this happen? There are basically two reasons why icy cores grow bigger than rocky cores, and one is related to the Stokes number and to the sizes of the pebbles, and the other is related to the pebble isolation mass. So let's go to the first one. Here in this plot, I'm showing the profile of the disk, the Stokes number for different disk viscosities, and you see here a clear jump that occurs at the water ice line. So pebbles that are icy, that are beyond the water ice line, have a larger Stokes number the Stokes number depends directly on the sizes of the pebbles. So this distinction happens because beyond the ice line, the pebbles that are icy are more sticky, are more difficult to break, so they can grow to larger sizes. And that's what gives a larger Stokes number. And the Stokes number enters directly into the accretion rate of the cores. The larger the pebble, the more rapid is the accretion by the core, because the pebble can be slowed down more easily by friction when crossing the proto-atmosphere. So in other words, so icy pebbles are larger. This means larger Stokes number. This means that these cores can grow faster by accreting icy pebbles compared to rocky pebbles. But the icy cores can not only grow at a faster rate, they can also reach a larger value because of this pebble isolation mass. So when a planet grows by pebble accretion, it cannot grow forever. There is a limiting mass for the cores, which is this called pebble isolation mass. It happens when the planet at some point perturbs the disk, creates a pressure bump beyond the orbit of the planet, and the pebbles at the pressure bump are stuck and cannot drift anymore, so they cannot be accreted anymore by the protoplanet. And the behavior of this pebble isolation mass goes like this. And just to look it in the profile of the disk, at larger orbital distances, a planet can reach much larger pebble isolation mass than at short orbital distances. So also beyond the ice line, the cores not only grow faster, but also they can reach a larger mass by this larger pebble isolation mass. So this explains why we see this dichotomy in the masses of the core when they are rocky, pure rocky, or icy. And as I said, we see that when we run our complete population, and we can see that again in a histogram of when we look at the masses of the core of dry planets versus wet planets. And this dichotomy in the masses of the core, when one with very simple mass radius relations computes the radius of these cores, we get actually the bimodality that matches very well what is observed in the Kepler exoplanets. So we have a first peak at 1.3 and a second peak at 2.4, and the radius between 1.5 and 2 of radian. But as I said, these planets, this is only the cores, and the planets accreted some atmosphere, and that then can be completely stripped by photoevaporation. So what happens when we look at the results of the full planets, including the atmospheres and the photoevaporation? We still see that thanks to photoevaporation, the atmospheres are stripped and the valley is preserved at the correct location. But the second peak of planets gets a bit wiped out because many of these cores actually retain too much gas, and they form here this peak that this is not consistent with observations. But there are many mechanisms already published that can account for extra loss of gas during accretion and also during evolution. So after this dispersal, one mechanism is giant impacts. We also tested this, including a simple prescription. And when the collisions are taken into account and the mass removal by collisions is computed, we again recover much well the two peaks. And also we start to see a very good overlap in terms of with the exoplanets known here are in gray color, and the other colors are just synthetic planets. So you see that we start to get a very good overlap between observations and synthetic or models. And here is the valley. So just to sum up, due to the change of pebbles properties at the water ice line, pebble accretion leads to two distinct core populations, icy and large versus rocky and small cores. And such bimodality from birth leaves a valley imprint on the size distribution of short period exoplanets. Atmospheric escape after formation must take place to get the bare cores of the first peak. And so both formation and evolution are important. And processes to hinder gas accretion and or to promote atmospheric escape must take place to account for the second peak. Also to get a better agreement with the mass radius of the observed exoplanets. And just for discussion maybe, so what can TESS do to test this scenario? Are second peak and valley exoplanets really water rich or predominantly water rich? And luckily TESS observes bright stars, which makes most of the exoplanets that it observes amenable to atmospheric characterization. And as we heard in 2 talks ago, this will help to lift the generacy for second peak exoplanets where this it's very hard to disentangle by mass and radius if they are rocky with hydrogen helium atmosphere or if they are rocks plus ices. There are interesting targets and systems already published where this could be done, hopefully soon. And we will hear more about this. You will hear already for Nu2 Lupi, and we will hear later also in the week or other cases. And also for the particular case of planets falling in the valley, those are very interesting targets because they should have lost the hydrogen helium. That's why they are in the valley. And this means that if we can get very accurate determination of the masses with mass and radius, we might be able to disentangle if they are really rocky or they need some lighter component like water to explain the mean density. And there are already about 140 TOIs in this radius, so it would be great to get masses for this. Thank you.
I had to find my mute button. Great talk. I learned a lot. Did I hear you say the word migration any place in the talk?
Yes.
But it didn't seem to be a dominant mechanism.
Migration is important to bring all these planets close by. Otherwise, all the water-rich planets that we form would stay. We would not observe them. So it's very important actually. I didn't speak a lot about it, but it's a key ingredient to bring them close in.
So Will Meissner says, great talk. Do your models attempt to reproduce the period dependence of the radius valley?
Yes, that's an excellent question. At the moment in our simulations, we are only able to study growth of one embryo per disk, and they typically end close to the disk inner edge. So most of the simulations I show, planets have typically a period of 10 days. And so to study the dependence on the period, we will need to have an M-body and see how these planets get trapped in motion resonances and end up at different periods. So this is work in progress. This is still not possible with this setup. But it's been now done with other codes in Bern, and they are starting to see also this dichotomy of icy versus rocky for the two peaks with M-body.
We're getting lots of good questions here. Michelle Kundimoto asks, will this work be able to distinguish between core-powered and photoevaporation-driven explanations for the radius valley?
That's also a great question.
Yeah, all the tough questions.
So yeah, it's tough. In our simulations, we are not including core power mass loss, but of course, it would be desirable in the future to include all these ingredients. To my understanding, core power mass loss would affect over longer timescales, so giga-year timescales, the evolution. So when there is more data about the age of the systems, then, and that will happen for sure with Plato, then I think it will be possible to really see differences at different times of systems, and then disentangle what is the dominant effect.
Right. Well, there's more questions, but I think you can go to the Exoplanets channel on Slack and answer them at your convenience. We need to move on.
Okay.
And hear about citizen scientists, I guess we call them. Well, I don't know what you call them, Nora. Why don't you tell us? Planet hunters. So I see your.
Sorry, I had to unmute myself.
Go ahead.
Great. Okay, I assume you can see my slide and hear me. Great, well, thank you everyone for listening to my talk on how we can find exoplanets with the help of tens of thousands of citizen scientists. So starting with the planets found by Kepler, when we look at their properties, we can see that inescapable bias towards the shorter period transiting planets. And that's no different when we look at the TOIs and the confirmed TESS planets. As we can see on the slide here, where over 90% of the TESS objects of interest found to date have orbit periods shorter than the duration of one TESS sector. Now with Planet Hunters TESS, we try to address this period bias by looking for longer period single transiting planets using visual vetting with the help of citizen scientists. So Planet Hunters TESS is a citizen science project that was inspired by the original Planet Hunters project, where the original project used Kepler data. But I designed and launched Planet Hunters TESS, which of course uses TESS data, at the very start of my PhD around 2.5 years ago. And since the launch of the project, it has had a very active community of nearly 30,000 registered volunteers who have completed over 18 million light curve classifications since December 2018. And when there is data on the site, the classification rate fluctuates somewhere between 30 and 70,000 classifications per day, meaning that all of those 20,000 monthly released 2-minute cadence light curves are regularly classified within just 10 days of the data release, which accounts for the spikes that you can see on this graph here. During the times when there is data on the site, however, citizen scientists can access it via our online interface that looks like this. So we purposely designed Planet Hunters TESS to ask us the one simple question, namely, do you see a transit? And for each light curve, this question is answered by 15 volunteers who will independently see this light curve and mark on any transit-like signals by drawing a box over them using their mouse. The results from those 15 individual volunteers are then combined using an unsupervised machine learning algorithm that ranks all of the light curves from a given sector from most likely to least likely to have a transit-like signal within the light curve. Now, for more details on how this algorithm works, please do see our method paper, Eisner et al. 2021, or of course, come and see me after this session. But for now, the most important thing about our methodology is that we rank all of the candidates for each sector. Now, this ranked list that we generate, amongst other things, allows us to assess the project sensitivity by looking at the rank at which TOIs are recovered. In other words, by seeing whether citizen scientists are able to identify the transit signals that the automated algorithms are able to pick up. So here we're using the TOIs as a test for our recovery efficiency by looking at the fractional recovery rate of TOIs at a given rank for each sector. So for example, if we look at the top 500 highest ranked candidates, we recover around 50% of the TOIs. Okay, 50% isn't bad, but if we restrict ourselves to TOIs with radii greater than 4 Earth radii, we recover 85% of them within the top 500 highest ranked candidates. So what this shows, of course, not surprisingly, is that visual vetting is very sensitive to the depth of those transit events. Now we can break the detection efficiency down even further by looking at the recovery rank of TOIs as a function of the signal to noise ratio of the transit events and as a function of the period of the planets, where a lower rank on this figure or a lighter color of the markers means that more volunteers identified that given TOI. So this figure shows that we are able to recover 90%, so almost all of the TOIs that have transit events with a signal to noise ratio greater than 7.5, which you can see indicated by that red line. But the really important thing that I want to highlight from this figure is that while we are sensitive to the signal to noise ratio of the transits, we are not sensitive to the orbital periods of the planet, meaning that volunteers are equally likely to detect a single transiting event as they are to detect a planet that transits multiple times within a given data set. And this is really important and really exciting because this allows us to identify those longer period planets and to start addressing that bias that we talked about at the very start of this talk. So for the last couple of slides, we've been talking a little bit about the detection efficiency of visual vetting and about the recovery of TOIs. But of course, we also find candidates that are not on those TOI lists. So we identify these new planet candidates by visually inspecting the top 500 highest ranked candidates per sector and by generating our very own data validation reports for them in order to identify true planets and rule out false positives. So these data validation reports are generated using LATE, or the Light Curve Analysis Tool for Transiting Exoplanets. And very briefly, LATE is an open source Python package that I developed last year that performs standard diagnostic tests in order to help identify, vet, and characterize signals in the TESS light curves. Now, I designed this tool with both citizen scientists and professional astronomers in mind, meaning that it has a graphical user interface and absolutely everything from downloading the data to generating the PDF summary reports at the end is completely automized. And for more information on this tool and how to use it, I want to point you to the accompanying JOS paper, or of course the GitHub page where you can download this tool and try it yourself. But having completed this manual vetting stage with LATE for the top 500 highest ranked candidates, we're usually left with around 3 high priority planet candidates per sector. Meaning that since the launch of the project, we've identified over 100 new planet candidates that were either ignored or missed by the automated pipelines, which you can see on this figure here, along with the TOIs, where the TOIs are shown in blue. And as you can see from this figure, the Planet Hunters TESS candidates are quantifiably different to the TOIs, where the Planet Hunters TESS candidates have systematically longer orbital periods, pushing past that 27-day orbital period threshold and allowing us to start addressing that period bias. And we're able to do that because visual vetting is sensitive to those single transiting planets, which make up the bulk of our sample. Now, as Natalia already mentioned, we're also now finding that multiple of these single transit events from the first years of the TESS mission show additional events in the extended mission. And with a combination of transit modeling and ground-based photometric observations, we're now trying to rule out some of those period aliases. Now, in addition to these ground-based photometric observations, which we're obtaining, we are also currently following up around 40 of our brightest targets using both spectroscopic observations and high-resolution imaging, of course, with the overall aim of further ruling out false positives and confirming the planetary nature of our candidates. So to date, we have successfully confirmed and published 2 of our systems. The first is a Saturn-sized planet around a subgiant star on an 84-day orbital period. And the second is a bright 2-planet system with a Neptune and a sub-Saturn-sized planet. And for today, I just want to talk about the latter of those 2. So HD 152843 is a bright early G-dwarf with 2 planets, one of which, planet C, only exhibits a single transit event in the light curve, as you can see on the slide here. Now, we followed the system up spectroscopically using HARPS North and ESPRESS, and with the data that we've obtained so far, we have an almost 3 sigma detection of the inner planet with a mass of around 11 Earth masses and an upper mass limit of around 20 Earth masses of the outer planet. But we are continuing to follow the system up using HARPS North and hope to be able to fully constrain the masses of both of these planets very soon. But even with the initial mass measurements that we have so far, we can very tentatively plot them on this mass radius diagram, of course, still with very large uncertainties. But even with the very large uncertainties that you can see here, these 2 planets stand out as having very low bulk densities, which suggests that both of these planets have extended gaseous envelopes, making both of these planets prime candidates for future atmospheric characterization, which is something that we're looking into planning ahead for when JWST launches. Now, even though multiplanetary systems are intrinsically not rare, Kepler found hundreds of multiplanetary systems. Systems like this one and the one that Laetitia presented earlier stand out due to their brightness. So this system here has a V-band magnitude of 8.8, making it an ideal candidate for comparative planetology. So studying and characterizing the properties of the planets that are formed out of the same material and at the same time, but are formed and evolved in different environments, which has in turn resulted in different planet masses, different radii, and different compositions. Now, all of our systems, including this one, are of course found with the help of citizen scientists. So the volunteers who were directly involved with identifying this candidate became co-authors of that discovery paper. Now, for the next part of this talk, I want to pivot away from planets entirely just for a couple of slides and highlight to you that 30,000 pairs of eyes visually inspecting TESS data has many exciting byproducts. For example, we have identified over 10,000 eclipsing binaries, which are being used as part of the TESS eclipsing binary catalog. And that's work that's being led by Andrew Persia at Villanova University. Now, unfortunately, I don't have time to talk about all of these eclipsing binaries. So instead, I want to present to you a triple system that I'm particularly excited about at the moment and on which we recently submitted a paper. And that's TIC 4707 10327. So this system, the stellar system, initially came to our attention due to the multiple periodic signals seen in the TESS light curve. So we have a 1.1-day binary as well as an interlacing 9.97-day signal. Now, even though the system was initially identified because of those 9.9-day eclipses, we now believe that they most likely belong to a background eclipsing binary. So even though I just introduced them, I want you to completely forget about that 9.9-day signal again. And instead, I want us to take a closer look at that 1.1-day binary. So careful modeling of the timings of the midpoints of those 1.1-day eclipses revealed a trend with a period of around 52 days. Now, this same 52-day periodic signal was also recovered in the radial velocity observations, which we obtained over the course of a year using the Hermes spectrograph on Mercator and La Palma. And as we see that same 52-day trend in both the eclipse timing variations and the radial velocities, we can confirm that we're looking at a triple system with a 1.1-day binary and a 52-day tertiary. Furthermore, dynamical modeling of these signals, combined with spectral typing of the stars, revealed that we're looking at a very rare stellar configuration, wherein the tertiary star, with a mass of around 15 solar masses, is more massive than the combined mass of the inner binary, making this a very interesting system in terms of its formation. But it's even more interesting in terms of its future evolution. So this is the triple system that we have at the moment, with a significantly more massive tertiary. Now, as that tertiary continues to evolve and enters post-sequence evolution, its radius will expand. And due to the compact configuration of the system, this will result in a phase of mass transfer from the outer star to that inner binary, which will eventually lead to the 2 stars in that inner binary merging, transforming that former triple system into now a binary system. That former tertiary star, however, will continue to evolve, and due to its initial starting mass, will end its life by undergoing supernova and turning into a neutron star. Sometime later, the other star will also evolve beyond the main sequence, likely resulting in a further period of mass transfer, this time transferring mass back onto that neutron star. Which brings us to the final and exciting stage in the evolution of the system, where we are either left with a neutron-neutron star binary, which of course is a gravitational wave progenitor, or alternatively as an exotic Thorne-Zitko object, whereby that neutron star is completely engulfed by the stellar companion. So needless to say, the system has an exciting future ahead of itself, and it's going to be a wonderful couple of mega years, so do stay tuned in what happens next. Now, finally, I want to end this talk by mentioning the future evolution of Planet Hunters TESS. As I'm starting to write up my PhD thesis, which will hopefully be on a shorter timescale than the system that we just talked about, I'm still making plans to continue with and advance the project. So as I mentioned at the very start of this talk, we have significant proportions of the month where the site has simply run out of those 2-minute cadence TESS light curves. We're therefore looking into filling those times with a selection of full frame image light curves instead. So within the next couple of weeks, we will be starting with a sample of bright young stars and bright post-main sequence stars that we're currently in the process of pre-selecting in collaboration with various other teams. And we're hoping to upload those very soon. But if you have any other samples of stars which you want to search for either planetary or stellar signals, I would love to talk to you more about that after the session. And in summary, Planet Hunters TESS has shown that we can identify and characterize a novel sample of planets and stellar systems with the help of a very large and active community of citizen scientists. And we hope you stay tuned for our future work with the TESS full frame images. And with that, I'd love to answer any of your questions.
Impressive how you have organized 30,000 pairs of eyes, did you say? Wow. In fact, do you have turnover amongst the people that are doing this? Do they get bored or do they just keep doing it?
Yeah, we have quite a nice distribution of people who just do a couple of classifications, and we have other volunteers who have classified every single light curve, and it's very, very impressive. They must spend a lot of time looking at TESS data.
So Emily Saffron says, I love being able to see how much the longer periods of your candidates are compared to the mission candidates, but she has a question. I should know this, but when you say 50% recovery, are you saying you recover 50% of individual signals from TOIs or 50% of TOI objects by some other particular definition of recovered, i.e. at least one signal from the TOI?
So we recover 50% of the TOIs, so irregardless of how many signals, how many transit events there are within the light curve.
Right. Hello, Nora. Excellent talk. Are most of the single transits queued for ground-based observations?
Not yet, but so we're talking to the NGTS team and hope to be able to schedule some more of those. At the moment, we're following some of them up using LCO, but not all of them by any means. They take up a lot of telescope time trying to track down when those other transit events are. So only a small sample at the moment.
One last comment from Kim McLeod, Wellesley. Thank you, Nora. Students in my introductory astronomy classes get so excited about being able to contribute to scientific research through PhD. I will use your PhD detection efficient slides when I teach them about it. So you've got some people out there to appreciate what you're doing.
Oh, thank you.
And it's very nice that you give credit to the people involved in the discovery, putting them as authors. I think that's great. All right, we better move on to the final scheduled talk of this section. And that's going to be Karen Collins, who is the lead for SG1. And there's so much she's been doing and so much she could cover. I don't know how in the world she's going to fit it all into 15 minutes, so I better stop talking.
Yeah, and I'm going to jump straight in because I do have a ton to cover here. We're currently 350 members strong across the world. That's out of the 500 total TFOP members that George mentioned. 350 have joined TFOP 1. A lot have are in multiple groups. If you're a newcomer, TFOP SG1 is time series photometric follow-up. Our goals depend on the depth of the transit. For less than 500 to 700, or for deeper than 500 to 700 ppm, we attempt to confirm the event on target. For shallower events, we try to clear the field of NEVs. And for a little bit deeper events, we try to do chromaticity checks. Once these goals are met, I basically turn off the TOI for further SG1 observations, except in the case of TTVs or in the case where folks have asked for additional observations. So this brings me to the point where I want to bring up to TESS contributed paper lead authors to please consider all the data available on ExoFOP. Please log in to see all of the data on ExoFOP. Your TFOP credentials will let you see all of the protected data too. Everyone has been really, really good about this, so it's greatly appreciated that the SG1 work gets recognized. But if you have additional observations you need, please let me know. On the flip side, if you have everything you need for the paper, let me know that, and I will inform the SG1 team and turn off the TOI, because we have plenty of TOIs to observe. Currently, there are over 6,500 SG1 light curves uploaded to ExoFOP. About 3,000 of those light curves are from LCO-GT. That's from the mission funded time, from the TESS follow-up LCO key project, which is led by Avi's 4, and see poster number 2.06 for more details. And there are a few SG1 members that have had some LCO proposal time as well. There are about 4,000 light curves reduced with AstroImage-J. And I mention this because the original intent of this talk was to discuss how to access that data, which I will still do at the end, but it will be in more of a summary state. One new thing that we have as part of SG1 is the Gaia TESS collaboration. And this is led by Aviad Panahi, Shay Zucker, and Zvi Mesa from Tel Aviv University. Dave and I meet with them when they have new results. We look through the Gaia light curves. The light curves are unpublished, so they can't be released as part of this. But they can tell us whether they're on or off target, the number of data points that were used in and out of transit, and the depth that Gaia found. And even though they can tell us NEB, we still don't know exactly which star is the NEB. That part cannot be identified. There's a poster on this. Please look at it, 2.07, to learn more. You can see a couple of examples where an NEB was identified on the right-hand side, and an on target was confirmed here. And keep in mind that Gaia's kind of got the 1 arc-second precision on being able to discriminate stars too. So another technique, if you're on the SG1 Google group, then you've probably seen this crazy word SAFIs, and we use it as sort of a centroiding technique in a way. We use it for QLP TOIs where there's no centroid information provided, or where it's unclear. This is an AstroImage-J technique. We basically load up apertures at the positions of all the Gaia stars that are bright enough to produce a TESS detection, and we create light curves for all of those stars using a 1 pixel aperture. So this is essentially the same as 1 pixel TESS aperture light curves, except the apertures may not be placed exactly on 1 single pixel. We get about 20 arc-second resolution with this method. 2 people have sort of taken over doing this now. The part of the SG1 team is Greg Serdok, who is a citizen scientist, and Gavin Wang, who is a high school scientist. And they've both contributed a lot. Gavin Wang is currently scripted AstroImage-J to automatically run SAFIs. So see Gavin's poster 1.06 for more details on SAFIs. We have a host of tools that have been developed that are probably generally useful for the community, and they're available to any TFOP member. You don't have to be an SG1 member, but there's the TESS Transit Finder and the SG1 Aladdin Field of View tool that Roland mentioned earlier. These tools were contributed by Eric Jensen from Swarthmore thank you so much, Eric. I know you know how much I appreciate the work you've done on these. And then there are two other tools, the TESS Observation Coordinator and the Gaia to Aperture tool that was put together by John Kilcoff from University of Louisville. Thank you to John for that work. The whole system is driven off of the SU1 TOI list, which is a Google spreadsheet. Anyone can have access to this by clicking the link. This is linked on the publications page. It's also linked on Exofop. And you can look through this list. There's an entry for every single TOI. You can see what the dispositions are. There are 3 different dispositions, a master, a photometric, and a spectroscopic disposition. Those are all defined. You can look on the dispositions tab. But if you really don't want to fool with the dispositions, read the comments. Sorry. Just read the comments and you can get an idea of where things are at. Once a TOI becomes either a planet or a confirmed false positive, these comments will be copied to Exofop. There's also this category of APC. It's called ambiguous planet candidate. You can almost think of it as a probable false positive, but not a guaranteed false positive. That's a category on Exofop as well. There are 2 more tools for lead authors. These are also linked on the publication sheet. There's LaTeX ready public author information here for all SU1 team members, and also instrumentation specifications for all SU1 team members. Again, so let's look at Exofop. We upload everything that we do to Exofop. Most people use the 1-year proprietary period, so please do log in to see all of the data. So the files can be sort of overwhelming. The best way to deal with that is to look at the observation summaries at the top. In this case, there are 2 observations. So let's look at specifically the LCO observations here. So the best thing to do is to click the tag number to the right-hand side. That tag number will then filter out and present only the data files associated with that observation. Now, that still leaves us with a good number of files, especially if the data were reduced with AstroImageJ. There's a reason for that, and I will explain that. But quickly, the easy ones are just the PNG files. You can see the light curve, you can see the field of views with the apertures overlaid, and a seeing profile. The meat, though, is in the measurements table. This is a huge file sometimes. It has a bunch of data columns, and that can sometimes be intimidating. All of these columns are defined in the AstroImageJ paper. But how do we get the data that you need for fitting out of that table? Well, there are several methods. The easiest is use something like Pandas and Python, or just a spreadsheet program, whatever you're comfortable with, and extract the column name BJD TDB, relative flux T1, relative flux error T1, and then any detrending parameters. And I would recommend just looking at the light curve plot to see what the person who reduced the data decided. And typically that's going to include at least air mass and sometimes full width half maximum. But these are the column names that you would want to extract from this tab delimited table. If you're lucky, the observer also created a data subset file. Those are labeled like this, like something like BJD flux error air mass.dat. These are ready for fitting. It's simply, in this case, only 4 columns, the BJD timestamps, the flux, the error, and the air mass column. If you want more, if you want to explore the data more, and this is why the measurements table is a little more complex than might be expected. If you combine the measurements table and the measurements plot config file, download those, open both of those into AstroImageJ, then you can deeply explore the data by customizing the comp star ensemble, see how different comp stars affect the light curve, see how different detrend parameters affect the light curve, and then you can output your own custom fitting file. You can either output the undetrended data plus detrend vectors, or you can pre-detrend the data in AstroImageJ and output that. There's a post on the AIJ user forum to explain step-by-step how to do this. And I'm going to get this posted on the publication wiki and possibly talk to the ExoFOP folks about posting it there as well. Just to make sure you're not too intimidated, AIJ is a completely GUI-driven tool. You just simply, you'll be presented with these panels when you open those files. You'll see the light curve plot. You'll see all the different comp stars that were measured. You can turn them on or off, which puts them in or out of the comp star ensemble. And in the fitting panel, you can enable or disable different detrend parameters. And you can see the plot and these statistics values get updated in real time as you change these values. So you can examine more in depth what's going on with the light curve, and then you can produce your own data subset plot from within AIJ. One more set of files I want to talk about. These are the NEB check files. These are in a zip file or tar file, usually with the word NEB check on them. They are light curve plots of all of the stars within 2.5 arc minutes that are bright enough to have caused the TESS detection. Again, these are extracted from John Kilcoff's tool, which is just a website, and then these apertures can be imported into AstroImageJ. It's actually just a text file with ARIA and DEC in it, so you could use it with any tool, any pipeline. Within AstroImageJ, though, Dennis Conte contributed code to build these plots for every star, and overlaid on the plots is a toy transit model that shows how deep the event would have to be in that star to produce the TESS detection. And over here on the right, you can see this particular star, what turned a TOI turned out to be an NEB, and you can see the depth is approximately what it was predicted to be. So you can just download that zip file, unpack it, and you'll see a different PNG file for every star within that field. Sometimes that's hundreds of stars. Quick plug, AIJ version 5 is now in beta testing. We have a George Mason University postgrad, Kevin Eastridge, that's working on it in depth. I work with him as well, and we hope to get that published in the next 2 to 4 weeks. And there'll be a lot of new capabilities and focused on automation and scripting capability. So the last thing I'm going to discuss is some of our citizen volunteer awards. I want to present to some of the SG1 team members. I have excluded purposely students, postdocs, and professional members because we all have interest in working with TESS for either academic or professional reasons. Our citizen astronomer volunteers do it. I will defer to them to tell us exactly why, but it just seems to be an intense interest in exoplanet science, interest in TESS and supporting TESS, and just wanting to learn, the curiosity, the general scientific curiosity. So a qualifier, these are strictly based on the number of ExoFOP TESS uploads. I'm trying to make it as impartial as I can. If I messed up, please let me know, SG1 team. I don't want to leave anybody out. But beyond this, I want to let folks know that there are many, many other extraordinary contributions. So if you're not on the list that's coming up, please know that I still appreciate your work, and that there are newer members who are quickly building numbers and their skills are going through the roof. So please stay tuned, possibly for additional recognitions at future meetings. So in the spirit of the Olympics, The bronze medal goes to TG Tan from PEST Observatory. It's his private observatory. TG Tan has uploaded 349 of his light curves to ExoFOP, and you would be amazed at the precision he gets with his small telescope. I think it's probably leads the world in precision from small telescopes. I know that TG Tan is somewhere out in northwestern Australia right now. TG Tan is in Western Australia, his observatory, but he's not online today, but we will contact TG. Coming in with the silver medal is Chris Stockdale. He also has a private observatory named Hazelwood, but he also contributes to the LCO Key project. To date, Chris has uploaded 391 light curves to ExoFOP. Thank you so much, Chris, and in particular from the Key project team that I'm a part of. Thank you for your significant contributions to the Key project team. Finally, with the gold medal is Rick Swartz. Rick is also associated with a private observatory, but I know from reviewing all of Rick's precise work that he contributes a very significant amount of his time to the Key project and the LCO data reductions. He's now uploaded 563 light curves to ExoFOP. So think about it, there were like 6,000. So Rick has single-handedly uploaded about 10% of all of the light curves that are on ExoFOP. Thank you, Rick. I don't know how to thank you enough though. We will get you your physical awards. Please send me your physical addresses so that the conference can get those to you. And this was sponsored by the TESS conference too, and Avi helped arrange this. So thank you, Avi. And a special thanks to Kevin Collins, who on a daily basis goes through all of our LCO observation requests, organizes those, and organizes the LCO analysis team. And that's it, except to thank the amazingly productive full SG1 team. Please keep it up and go TESS. Here's to hopefully many more extended missions.
That's an amazing accomplishment from SG1, from a very large number of people who are doing it just for the love of it. And we used up all the time, Karen, so you don't have to answer any questions.
Okay.
But people can put questions into the Slack channel and you can take a look at them.
Sure thing.
Now, that was the end of our normally scheduled program, but we do have a bonus track. A breaking news, a second planet around LTT 1445A. You heard it alluded to a little bit ago from François. Jennifer Winters is going to spend a few minutes telling you about this second planet. And I see your slides.
Okay, great.
And I hear your voice.
Fantastic. Hi, everyone. It's really good to be here. I'm excited to tell you the story of the synergy between citizen scientists and professional astronomers in the form of an update on this LTT 1445 system. So just as a reminder, LTT 1445 is a triple M-DOR system in a hierarchical configuration at roughly 7 parsecs. The A and BC components are separated by 7 arcseconds or so. B and C are separated by 1 arcsecond. And in the test data, all 3 stars fall on 1 test pixel. Now, 2 years ago, I was thrilled to be able to lead the discovery paper where we reported a planet in a 5-day orbital period that transited the A component in this system. And at the time, when the paper came out, Marty Christensen contacted me with a message to the effect of, "We think you'll like your system better with a second planet." And he sent me this plot where this is the test light curve from sector 4. And in green is the 5-day planet that we had detected. And in amber is this a 3-day signal, which at the time we did not feel was compelling, and we chose not to follow it up. a year later, Sector 31 data was released from the TESS mission. And I show you the light curves from Sector 4 and Sector 31 here in these top panels of these plots. So not only are there 3 stars that contribute to the light of this to this light curve, but also there's a rotational modulation where star spots are rotating in and out of view on one of the stars. There's also flares in the system from one of the stars. So Amber Medina took over the analysis where she used a Gaussian process to account for this and fit the stellar activity while preserving the signal from the planets. And here in the middle panels, we show in purple is the 5-day planet, which we had just published, but we also recovered the 3-day planet signal. But again, we know we were able to confirm with ground-based data that the 5-day planet transited the primary star in the system, but there's 2 other stars in the system, and we didn't have ground-based data to confirm which of the 3 stars is the host star of this new signal. But at the time, I was working on the mass determination of the 5-day planet, and I was privileged that 5 separate high-resolution spectrograph teams shared their data with me so that for that purpose. And these are radial velocities from ESPRESSO, from HARPS, HiRes, MaroonX, and PFS. So all these amazing instruments with really great high-quality radial velocities. And we investigated the residuals of the fit from only the 5-day planet, and with that signal removed, we see a significant and very compelling signal at 3 days. And I want to just emphasize that these instruments are on telescopes that are able to resolve the A star from the BC pair. So these are radial velocities only of the primary star in the system. And so with these results, we are confident that the 3-day planet also transits that primary star in the system. I want to just point out right now, François Bouchy earlier presented the ESPRESSO GTO's early results on this system, and they're leading a separate analysis with many more ESPRESSO RVs than I have access to. But that's a work in progress, I mean. So we measure the mass of both planets using all 5 spectrographs data. I show here the masses that we measured. We also needed to account for the orbit of the stellar triple, so A and BC. There's some kind of imposes a trend in the radial velocities, which we had to include in our model, shown here in this gray slopey line. We also refine the radius of the 5-day planet here on the right-hand side, and we measure a lower limit on the radius of the 3-day planet. Now, the shape of the transit is still uncertain, and that's just due to the shallowness of the transit depth and the low signal to noise of the light curve. These are 2 of the most spectroscopically accessible planets for atmospheric studies. I show them here with a selected rocky planets. And then just in summary, this is the 2nd closest transiting system known and the closest one that transits an M dwarf. We measured very precise mass and radius for the 5-day planet, which allows us to estimate a core mass fraction and place it on this mass planet radius, mass radius diagram, where the 5-day planet lands very squarely on the rocky compositional curve, and the 3-day planet is, if it turns out that the radius is actually the lower limit, it also would turn out to be rocky. We've discovered this new planet with a 3-day period, and these are 2 of the most spectroscopically accessible planets, and we're excited to get JWST data on these. So the paper is posted on the archive. It came out last night, so please check it out, and I'm happy to take questions. Thank you.
Congratulations, Jen, to you and the team.
Thank you.
Great stuff. I think probably, unless we see pressing question. Oh, there's an easy one. Did I miss which star the 3-day planet orbits?
It's the primary star.
Right. That's where the action is. Good thing too,
Right.
because the 1 arc-second pair would be really tough to study with PRV.
Yes.
So great. That's the end of this session. The next session begins at 19:30 UT, which means
Dave?
yes.
We have a brief announcement or two.
Okay, I was just going to make that first announcement for you, but I'll let you take over.
Jen, you can take over.
Oh, yeah. Sorry about that. Sorry.
No, I mean, sorry, Jennifer Burt, you can take over.
Too many gens on the line. Yeah, thank you, Avi. I wanted to hop in briefly on our first exoplanet session just to make people aware that this coming Wednesday, August 4th, we're going to be having a rollout event for the NASA and NSF Extreme Precision RV Working Group's final report. So this is a team of about 50 scientists from around the world, and throughout much of 2019 and 2020, we were working on trying to put together a report that was commissioned by NASA and the NSF to advise on the best ways to try and reach the RV precision level needed to precisely measure the masses of Earth mass planets in the habitable zones of sun-like stars. And so there was a lot of work that went into this amongst all the people pictured here and many others who were part of it. The final report is now available. It has been posted both to this website and it came out on the archive last night. The full report is 100 pages long, but there's a very nice executive summary that's about 7 pages long and a little more tangible for folks to jump into and get through in a timely manner. And so we're going to be discussing the highlights of the report this Wednesday for about 20 minutes of this hour-long town hall, and then it's going to be 40 minutes of Q&A with the community. We'll have some of the report authors there, along with many of the working group members on the line. And so if you're interested in hearing about recommendations for how to move towards detecting Earth analogs, this is kind of in support of upcoming direct imaging mission concepts such as HABEX or LUVOIR. Feel free to tune in. There'll be plenty of time for discussion, and we'd love to hear your thoughts and try to clarify any points that are not clear in the report itself. I'm going to put the connection info in the Exoplanets channel of our Slack, but please feel free to reach out to me if you have any other questions, comments, concerns about this. I'd love to chat.
Yeah, thank you, Jen. I just want to take the time to briefly walk through the GatherTown tool or space. So those who are familiar with GatherTown or who are not interested in GatherTown, feel free to leave. There is nothing in this session beyond this very quick walkthrough. So once you click on the link for GatherTown, you'll see this monitor or screen. You can, this is your avatar. You can go and change how your avatar looks like and the clothes. You can put on a little bit your own personal taste here. And you can also, your display name, you can change it up here and click on next. You can turn on your camera and your audio here. I'm turning them off because I'm using it to connect on Zoom and join the gathering. And you go into what we call the main room of the GatherTown space. So this is me. Just you use the arrows to walk around, and you can see a few people around here and all the users that are logged in here. And but you immediately see that there are 9 poster halls, and each of them has up to 24 posters. So first, to see the list of posters, you walk up to this one of those 3 like boards or podiums, click on the X, wait a few seconds, and then eventually the list will show up. Okay, it did. So this is a Google spreadsheet. There is also a link to it from the website itself. So you can see the poster ID and the details of the poster. And of course, there are many, many posters, almost 200 of them. And the poster ID is, of course, the whole number dot poster number. And we can go out of here and just go to a random poster hole and go click on a random poster. You walk up to it, click on the X, and the poster shows up. Note that you might need to scroll down a bit to see the full poster. So this is basically a PNG version of the PDFs that were uploaded to Zenodo. So those are the posters. A few more things that we have here. If you walk south, you can go to the beach, and maybe you can hear the waves. I'm not sure if the audio transfers from GatherTown into Zoom, but there are waves heard here. There is a piano you can play here. It does work, and there is some video games here you can play. One or two more things. You can go up to the roof where there is a small campfire here. Maybe you can hear it. And one last thing, there is a TOI help desk here where during the poster sessions, someone from the TOI team will be staffing this help desk. So you can walk up to the help desk and actually ask questions in person about the TOIs. Oh, one last thing I missed. Down here, there are breakout rooms. If you want to have a small group meeting, you can use this room, get some virtual privacy. And there is this board. You can click on the X, and then you can really like make whatever. Yeah, you can just scribble on the board. Just make sure to, leave it clean when you exit the room. I think this is it. If you have any ideas, actually, what to add to this space, feel free to let us know. This is open continuously up until August 13. And you can see the people around me. When the avatar is close to me or close to you, when you are here, you can see their camera and audio turned on. Just like in real life, you walk up to someone, you can see him and hear them. I think this is it. Again, this is probably the newest virtual online tool we are using in this conference, in addition to Zoom, Slack, YouTube, and Twitter. So all this was very new and strange to me about a month or two ago, but I learned to see that this is a lot of fun and very efficient, not only for viewing the posters, but maybe even more to the social interaction, which is something that is very, very missing in these online conferences. So I will stop talking here. By the way, to get out of, you just click back and you're out. This is the screen I'm seeing, but you will see a different one. Okay, that brings us to the end of the session. Thank you very much to Dave Latham for chairing the session. The next session starts later today at 3:30 East Coast time or 7:30 UT. And those who will not be able to join the later session today are welcome to the next session tomorrow at 9 a.m. East Coast time, which is 1 p.m. UT. And thank you all for joining.